Okay. The Department of Pure and Applied Sciences of Midnapore City College regularly organizes seminars where we invite scientists where we invite scientists of international repute. Encouraged by the success of previous seminars, both offline and online, this year we are again organizing another online webinar with topic recent advances in astrophysics and physics. Today we have three speakers, all of whom are one of the best in their respective fields. Our first speaker is Dr. Alok Gupta. We said 2 decades of personal relationship, as I know him from my PhD days. Dr. Alok Gupta is an eminent astronomer. He is a senior scientist from ARIES, Nainital. He is internationally famous for his work in active galactic nuclei. So today I will request Dr. Alok Gupta to start his presentation. Alok.
So, good afternoon. Can you hear me?
Yeah, we can hear you.
Okay. Okay, so today I will talk about multi-wavelength variability and QPOs, quasi-periodic oscillation in Blazars. So, I am Alok Gupta, work in ARIES, Nainital, and this is my institute building. You can see this is at top of the building. There is a telescope. This telescope has 1 meter diameter, 1.04 meter diameter. So where we are in the geographical location of India, if you see, these are the places marked with hill stations in India. So it is the closest hill station to Delhi. This is Nainital. So my institute is in Nainital, and this place is a very nice place to live. You see the maximum temperature variation is -5 degrees centigrade to 30 degrees centigrade. This place is neither extreme cold or extreme hot. So this is our field station, or we have another observatory which is in the Nainital district, but it is around 70 kilometers far from the Nainital town. And there we have 3 telescopes. This is the 3.6 meter telescope. Its aperture is 3.6 meter. This is the largest optical infrared telescope in Asia. And there is 1.3 meter optical IR telescope here we have. And there is another telescope, it is called 4 meter International Liquid Mirror Telescope.
Sorry to interrupt, Alok. Pardon me, Alok. Your front page. So can you just make it, you can see the other pages? Okay, yeah, now it's visible. Okay, you go on, carry on. Yeah, thank you.
Okay. Yeah. So this is the International Liquid Mirror Telescope. So this will be commissioned very soon. So here in the mirror we use Mercury as a mirror. So nowadays, if you see in the present day astronomy, time domain astronomy and transient universe is very hot topic in the astronomy. So what does it mean? Basically, it deals with explosive transient sources, means large range in energy and a time variable style. And nowadays, it is possible to do simultaneous multi-wavelength observation. So one can do simultaneous multi-wavelength astronomy. So these, if we club together, it is very helpful to understand complicated emission mechanism of transient sources. Transient sources there are several transient sources exist in the universe, like gamma ray burst, supernova, X-ray burst, ultra high energy cosmic rays, and blazars. So I will be talking about about blazars and what are the recent projects we have done or what people basically do. So in last few years of studies of transient sources as producing large number of research papers. So this is a very hot field, and many people working in astronomy works in different transient sources. Outline of my talk, I think most of the people don't know much about AGN, so I will give a detailed introduction about AGN and Blazars. I will just give 1 or 2 slides where you can get feeling from where we use ground and space-based data. And the result I have divided into 2 parts: single and multi-wavelength flux and spectral variability of Blazars on diverse time scales, and QPOs in Blazars PKS 2155-304 and B2 1530 plus 31. And then I will summarize the result. So basically astronomy, if you see galactic astronomy, so anything we study, any object we study in our galaxy, that is called Milky Way, which is a tiny part of universe. So this, anything we study in Milky Way, it comes under galactic astronomy, and beyond Milky Way, everything comes under extragalactic astronomy. So to study objects outside Milky Way, which almost cover complete universe, so full of various classes of fascinating objects like normal galaxies, active galaxies, exotic objects like GRBs and supernova, and different extragalactic objects emit radiation in different EM bands. But a tiny subset of a special class of extragalactic objects, I have put a question mark here, which I will tell later, emit radiation in the complete EM spectrum. So these type of objects are prime target for multi-wavelength astronomy. One can do simultaneous multi-wavelength or quasi-simultaneous or non-simultaneous. So this covers entire electromagnetic spectrum, and you will get the feeling if you want to put a telescope, where you have to put. Like if you see gamma ray, X-ray and ultraviolet, then you have to go in space. And for optical and radio band, you can do from the ground-based telescope. Infrared, you have to go much above the sea level or also in space. And when you want to do long wavelength radio observation, then again you have to go in space. So what are AGNs? Active galactic nuclei. Active galactic nuclei are basically nucleus of galaxies which show energetic phenomena that cannot be clearly and directly be attributed to stars. So what does it mean? Basically, if we see an astronomical image, it is very, one cannot distinguish which one is AGN and which one is star. So basic criteria is that you take the spectra of AGN in these objects, and then you can classify this is looks like a star spectra, this looks like a very different spectra than a star. So here, the AGNs are classified into several subclasses, classes, which I have listed some of the classes here. FR1 galaxies, CFERT 1.8 galaxy, narrow line X-ray galaxies, high polarization quasars, QSOs. So many subclasses are there, and you can see that these are the typical spectra for different classes. Like if you take BL-like object, it does not have any prominent emission or absorption line. If you go for mean quasar, general quasar, they show very prominent emission line. There are normal galaxies, you can see a lot of absorption line. And CFERT1 and broadline radio galaxies, if you see, they have similar type of features like broad emission line as well as narrow emission line, but they belong to 2 different classes. I will tell in next other slides. And CFERT2 and narrow line radio galaxies, they have similar type of spectra, but they belong to 2 different subclasses. So basically, AGN can be classified into 2 subclasses. Radio quiet AGN and radio loud AGN. So this classification is basically based on flux you take at 5 gigahertz. This is radio band. Divide the flux at B band. This is optical band. If it is greater than or equal to 10, then this AGN is called radio loud AGN. Only about 10 to 15% AGN are radio loud. So as I said, this type of sources can emit radiation in the complete EM spectrum. So we can generate a spectral energy distribution. And here you can see there are 2 SEDs, spectral energy distribution. This continuous one is for radio quiet and dotted one is for radio loud. So here you can see radio quiet objects don't emit in radio band, or if they emit, the emission is very weak. And radio loud, they emit in all bands. So you can see from infrared to optical, or even soft X-ray, this radio quiet and radio loud looks similar, but radio loud objects are more luminous in X-ray compared to the radio quiet. So AGN one can understood by this cartoon. It has a black hole, supermassive black hole at center. Supermassive means black hole mass is 10 to the power 6 to 10 to the power 9 solar mass, which is surrounded by an accretion disk, and there is a dusty torus of gas and dust, and here a cross section of torus is removed, so one can see this black hole accretion disk, and also you can see a lot of black dot and gray spots. So basically this black dot and gray spots are the regions from where you can see the emission spectrum. So this closer to the black hole, these regions emit the broad line region, and if you go further away, then these are the narrow line region. So according to this cartoon, one can classify this earlier two classes, radio loud and radio quiet, and which is shown in this picture. The upper half portion is showing the radio loud object, and below one is the radio quiet. So what is the fundamental difference? Radio quiet objects have jet, but radio loud objects have jet, but radio quiet objects don't have jet. So if you are looking along the jet axis, then it is called blazars. With modest angle, then this is radio loud quasars, and larger angle are the radio galaxies, broadline radio galaxies and narrow line radio galaxies. If we go to the opposite side, nearly perpendicular to the disk, this is radio quiet QSOs, and type 1 and type 2, they are Seyfert 1 and Seyfert 2. So now you can understand this is basically spectral property is similar like narrow line radio galaxies and Seyfert 2 and broad line radio galaxies and Seyfert 1. But these belongs to the radio loud objects and these belongs to the radio quiet. So my focus is mainly blazar. So blazar is a rare but most powerful class of AGN. Its property, they belongs to the radio loud AGN class, and when we club together BL-like object and flat spectrum radio quasar, then it is called blazars. So BL-like object, so featureless optical spectrum, and flat spectrum radio quasar, so prominent emission line in optical spectrum. They show flux variability in the complete electromagnetic spectrum. Their polarization is variable in radio to optical band because high energy polarization is not yet studied, and the emission is predominantly non-thermal, and they make the jet axis is angle is less than 10 degrees. Blazars are further classified into two subclasses, LBL or RBL. These are also known as red blazar or low energy blazar or radio selected blazar, and HBL. This is also known as XBL. These are known as blue blazar, high energy blazar, or XSR. Basically, red blazars, this one are discovered in radio surveys, and these HBLs are discovered in the X-ray surveys. And they show double hump SCDs. So this long dashed one is the SCD for LBLs, and dotted one is for HBL. So in LBL, first hump peaks in IR optical, and second hump peaks in the GeV energy. GeV is the gamma ray. And in HBL case, first hump peaks in UV and X-ray, and second hump peaks in the TeV energy. So low energy part is more or less well understood. It is basically synchrotron radiation, and high energy part is probably it is inverse Compton. So low energy part of SCD is well understood. Basically, it is non-thermal radiation in high energy state, high flux state, and thermal plus mixture of thermal plus non-thermal radiation in the low state. But in high energy part, SCD is not well understood. It is usually explained by as arising from inverse Compton scattering of the same electrons, producing the synchrotron emission. When these electrons interact with the synchrotron photon, then it is called synchrotron self-Compton. And when it interacts with external photons originating in the local environment, then it is called external photon. There are alternative hadronic models where gamma rays are produced. Basically, this alternative model, this is called hadronic model. It is only applicable for the very high energy gamma ray emission. So produced by very high energy protons, either via proton emission or via secondary emission by photopion or photopair production. So there is a lot of challenge to understand high energy part of a series of blazars, which can be better understood with the multi-wavelength facility. So why to study blazars? So blazars are basically multi-wavelength and multi-time scale phenomena. And the variability time scale, flux variability time scale, can be divided into three parts. Intraday variability, where time scale is several minutes to less than a day. Short-term variability, where time scale is few days to few months, and long-term variability is time scale is few months to several years. Here I have given example. This is intraday IDB light curve. You can see it is almost 8 to 9 hours continuous monitoring of this source, and you can see large change in the flux. This is a typical example of this short-term variability, where you can see this is about 12 days of observation of this source, and you can see large flux variation. And this is the long-term variability, which has a century-long data, 1891 to 1995, and you can see large amplitude flux variation. So these are the three types of variation. So major revolution in blazar studies are made due to Fermi and recent development in very high energy gamma ray facility. So I remember when this Fermi satellite was under preparation, then people were having this construction phase, then they were having a lot of different people have different aim to do science, but finally after launch of this, you can say that this is a dedicated satellite for blazar studies. So total, this is the catalog based on data collected till 2020. So about 62% of objects observed by Fermi are blazars and 28% is unclassified. So there are hardly any scope for any other class of object to study using Fermi. And there is another ground-based facility, which is Hess telescope in Namibia, where 37 institutes, 12 countries, and about 200 scientists, engineers, and students are involved. So this is an European facility in Southern Hemisphere. And after success of this facility, a similar facility is developed by Europeans called MAGIC, that is in La Palma. Veritas, this is American facility, and this is Indian facility, which is under commissioning phase. So there is another interesting discovery, neutrino emission from blazar, this one. So you can see how much this field has revolutionized. In 2005, there were total number of known TV HBLs were only 6, but till date this number has gone to 73. So what are the sources of variability? So variability in blazars can be intrinsic to the source, which can be explained by soft front in the jet. So this has the ability to explain variability on IDV and STV time scale. Instabilities or hot spot accretion disk. This explain variability in IDV and STV time scale and binary black hole model. So which has ability to explain variability on long time scale. Extrinsic is gravitational microlensing. There are a few blazars which are microlens system. So in that, IDV can be also explained by gravitational microlensing. And there is another reason of extrinsic variability is interstellar scintillation, and it is only relevant in the low frequency radio observation. So variability properties, if you see IDV light curves, so light curve looks irregular and non-periodic, and it is helpful to get the size of emission region and black hole mass estimation. STV, that is also irregular and non-periodic, useful to search for color variation. And long-term variation is quasi-periodic, useful to predict next outburst time, search for time lag in different energy bands. So these are the three different models. This is called hotspot on or above accretion disk. This model is given by Professor Sandeep Chakravarti and Paul Vita, and Arun Banglam and Paul Vita in 2 papers in 1993. So this has ability to explain the IDV and STB. But when you detect the quasi-periodic oscillation, then this model can we can rule out, because then the black hole mass estimation exceeds the limit of the AGN black hole mass. This is another model which is very popular model, and it has several versions of its modification. And this model is given by Blandford and Martin Rees in 1978, and now the leading group in Boston, that is Alan Marshall. And so where you can see the jet structure can be helical or irregular jet, which has ability to explain the variability on various time scales. And this is binary black hole model. This is based on OJ287. I showed the light curve of this source for 100 years. So this model was given in 1988, and according to this model, they predicted that this source should show a strong outburst in 1994 and 95 that was really detected. So from where do we take the multi-wavelength data? So here I will use two color coding. Red one shows the new observation and blue one shows the public archive. So for gamma rays, there are Fermi, LAT, where one can get the public archive data, and for tactic BRC, Mount Abu, we use our planned observation. X-ray observation are public archive data. There are several satellites, RXT, XMM Newton, Chandra, Swift, Sujaku, Maxi, and New Star. And for UV, there is Swift UBOT and OM monitor at XMM Newton. Optical NIR, generally we use 27 telescopes. So here you can see in SMARTS there are 4 telescopes, and Steward there are 2 telescopes from which data is publicly available. And Swift UBOT, OM XMM Newton, this data is also public. And there are a lot of observatories and telescopes around the globe. So from there we conduct new observation. And for radio, there are 5 single dish telescopes, in which from 4 we can plan the observation and get, and this OBRO is the public archive data. So now I will come to the first project, single and multi-wavelength flux and spectral variability of Blazars on diverse time scales. So if you see in a typical light curve, which type of features you expect it can be stable flux, decline flux, means decrease in flux, quasi-periodic oscillation, and flare. So here is a nice example. There is continuous 3 pointing by XMM Newton for this source. This is first pointing like segment 1, segment 2, and segment 2, first pointing, second pointing, and third pointing. And different color code shows different flux state. Like if you see 1A, here the flux is stable. 1B and 3A, the flux is decreasing. And in this segment 2, there is a QPO, and 1C, there is a flare, and 3B, there is a strong flare. So they can see large amplitude flux variation, which has nice evidence of jet and accretion disk based model. Similarly, for the same source, there are large number of XMM Newton observation. And you can see there are just, I have taken as a sample 4 observation, and corresponding time scale estimation is done here. Here you can see for this one, this is the structure function analysis, which is keep rising. It means the variability time scale is longer than the data length. Here there is a peak followed by a dip, peak followed by a dip. It means this peak is giving the variability time scale. And this one is very interesting, which I will show in the later. There is a peak followed by dip, peak followed by dip, peak followed by dip. So this showed a quasi-periodic oscillation, which I will show explain in the second project. Similar IDV examples you can see with the Chandra and New Star. There are various light curves. All you can see large amplitude flux variation. And these are, and now this is the spectral variation on IDV time scale. Here you can see simultaneous optical, UV, and X-ray data. And the same light, one color is showing the same date of observation fitted with two different models. Here we have fitted with the log parabolic model. And you can see the residual is very high, minus 200 to 200, something like that. This is for blue one, means 23rd 11 2004. This is the 11 2006 and 22 April 2007. So what we did, in general, people use log parabolic model for this type of studies, but what we tried an additional model, log parabolic plus power law model. And you can see this residual has drastic improvement, where it was minus 200 to 200, now it is minus 60 to 60. So we conclude that if we have simultaneous optical UV and X-ray SED, then power law plus log parabolic model is a better model. This is the on IDV time scale. This is the very famous source, Markarian 421. This is the brightest X-ray source in the universe, I will say. And if you see the slide curve, there is certain huge of X-ray flare is detected. This huge flare is zoomed here. A zoomed version is plotted here, where you can see double peaked outburst in Markarian 421. On STV time scale, it is hardly something like a week-long data, and strong double X-ray outburst is explained by jet-in-jet model, which this is the model which explained rapid X-ray and gamma ray variability. Similar STV for this is optical band for B, V, R, and I. These are four optical band. This is it was predicted by the binary black hole model that this object should show a strong flare in 2015. So we started a campaign from September 15, and still we are doing this. So this is the first paper in this series, which was based up to the data collected from September 15 to May 2016. And there are multiple flaring events. You can see here, here. There are multiple flare on is detected in this Blazar on STV time scale. This is an observational, multi-wavelength observational campaign. Here you can see optical BBRI, here 2.8 centimeter radio band, here 6 centimeter radio band from two telescopes, Effelsberg, Germany, and Urumqi, China, and this 11 centimeter. And this is the shift. So you can see large amplitude variation is seen. This is again on STV time scale. It is about 10 days observing campaign. And total change in optical band is 0.8 magnitude. That is quite large on this time scale. And here we have looked for optical versus radio correlation. There is no correlation. And here we have looked for radio versus radio correlation. So you can see there is a lag, because in the low frequency radio observation, in general, this is contribution by extrinsic as well as intrinsic, but high frequency, it is only intrinsic. And we have generated the SED and calculated the Doppler factor. This is the polarization study, optical flux and polarization. This is a very unique result where anti-correlated optical flux and polarization is found for the first time in the BLSRT. Here you can see there is a two observational season taken from 2008 to 2010, and this observation was carried out from Japanese telescope, a 1.5 meter telescope in Hiroshima. And you can see, while on visual inspection, we divided this is the flux, this is polarization, and this is polarization angle. So this is segment 3, and first session was divided from starting to here is segment 1, and this is segment 2. So this is the standard star cross correlation. You can see in segment 1 there is no correlation, segment 2 there is no correlation, but segment 2 there is anti-correlation. So this anti-correlation was found in this Blazar, and this is very unique result which can be explained by just varying the Doppler factor and fixing other parameters. This is another Blazar where multi-wavelength observation. This is gamma ray light curve, this is X-ray light curve, this is Fermi light, this is MCC, and this is optical R band ground based telescope data. This is this row you can just skip. This is soft band X-ray, this is hard band, and this is hardness ratio. And here we have looked for the cross correlation, where you can see gamma ray and optical are very strongly correlated, but there is no correlation in gamma ray and X-ray and optical. So in Blazars, we got a strong optical and gamma ray correlation with time lag of 4 days, where this is explained by external Compton emission mechanism. And this is a very interesting multi-wavelength observation of this source, where you can see this is the gamma ray light curve, this is X-ray light curve, this is optical polarization angle, this is optical polarization, this is optical and infrared light curve. This top one is infrared into J band, and this is V band optical, and this is radio. Here you can see a strong flare is seen in gamma ray, X-ray, and optical NIR during 2009, December 3 to 12. This is small portion. You can see a very strong flare is seen here. No flare in the radio, but this all. And emission in optical NIR band rose more gradually than gamma ray and X-ray through all peak nearly at the same time. Optical polarization showed dramatic change during flare with a strong anti-correlation between optical flux and degree of polarization. The similar result here, you see when the flux is high, polarization is low, and similar change in polarization angle also. So this combination of behavior appears to be unique. So here is the long-term observation of this source 3C273. You can see observation about 2000 to 2012, 12 years of data. Here, this is optical, UV and X-ray. This is soft X-ray and this is hard X-ray. So on visual inspection, you can see optical, UV are very well correlated, and soft and hard X-ray are well correlated. And here we have looked for the hard soft X-ray correlated, UV, optical correlated, UV correlated, optical and UV are correlated, but optical X-ray not correlated, and UV and X-ray are not correlated. It means flux variation in optical UV are not correlated with X-ray. It means optical UV emission of Blazar may arise from a different population. Means optical and UV are emitted by one population of lepton, and X-ray is emitted by the another population of leptons. So here we have looked for the hardness ratio with respect to time. Whole 12 years is divided into 5 segments, and where we have got this anti-clockwise and clockwise loop. So both clockwise and anti-clockwise loop represent synchrotron cooling and as well as particle acceleration. Work on different epoch of observation in this source. Now I will come on this another project, QPO in Blazar, PKS 2155-304 and 1520 plus 31. So presence of QPOs are fairly common in microquasars, but rare in AGN. So microquasar, this is a binary system orbiting each other. So one can say rotating, there is possibility of QPO. But in AGN, this is not a binary system in general. So what can cause the QPO? So there are these models. This model I showed you, hot spot on accretion disk can possibly explain QPO on IDB time scale. But this model rule out for STB and LTB time scale because black hole mass exceeds 10 to the power 10 solar mass. And another model is that where jet is propelled by magnetic field twisted by black hole accretion. That is called helical jet structure. That can explain the QPO on diverse time scale. So QPO reported in AGN before 2008. You can see there are 3 papers I have mentioned, important papers. And QPO reported in AGN since 2008. So these are two papers. These results, later QPO detection in all these papers were either found wrong or statistically not significant. So when someone is claiming QPO, should be very careful. And nowadays it is good to do QPO detection by multiple methods. And if the result confirms, then one can claim if there is a QPO. This is QPO time scale can be used to get the very black hole mass. And this is just a standard textbook material. And you can see this is the final equation. M by m dot is equal to 3 into 10 to the power 4. P is the period in seconds, and R to the power 3 by 2 plus A. A is the spin parameter 1 plus Z. For non-rotating black hole, R is equal to 6 and A is equal to 0. And for rotating black hole, it is 1.2, R is equal to 1.2 and A is equal to 9.9982. These are adopted from the textbook. So this is the so far the best case. Why I told 2009 divided into 2008 and before 2008 and 2008 after 2008, because this is the paper which appeared in Nature in 2008, and after then there are large number of QPO detection in different type of different agents on various time scales. So you can see this is the XMM Newton light curve of this narrow line Seyfert-1 galaxies, and whole light curve is divided into two parts, segment 1 and segment 2. So the detailed QPO analysis is done in segment 2, and they have got a 1 hour QPO and folded the light curve, nice sine curve you can see here, and they did power spectrum analysis, and this QPO detection is 5.6 sigma, which is so far the best QPO detection. This is another QPO detection in 3C273 in 2008, where wavelet analysis is used, and again the data was from XMM Newton, where 1 hour QPO is detected in this source. So we are working on the QPO also, and we have reported QPO in about a dozen of papers, and I will just show two results, but I can quickly go through. So first QPO result we reported in this Blazar S50716 plus 7154 on 5 occasions. There were around more than 100 optical light curves published for this source, and we put very strict selection criteria, and then the light curves which qualified our selection criteria, then we did wavelet analysis, and we got QPO time scale from 25 to 73 minutes with confidence level more than 99%. This is, we took complete sample of RXT SM data for all Blazars, and we looked for the QPO, and we got the QPO on in this Blazar on 17 days, that is STV time scale, and another Blazar on 420 days, and the result is verified by structure function, DCF, LSP, and data folding. This result I will show. This Blazar which I showed you, there is nice QPO pattern was there, where we got QPO on IDB time scale, and result is verified by structure function, wavelet, PSD, MHAOV, and data folding. In this source, we got 3.3 hours QPO and 1.9 hours QPO. I have written here it's a hint of QPO because number of cycles were very less. This is the observation we carried out from Mount Abu telescope, and we got the fastest QPO ever detected in any AGN. That is 15 minutes QPO, which is confirmed by structure function, power spectrum analysis, LSP, and data folding. In this source, we got weak QPO on this source, 1.1 day. Again, this was just 2 cycles. So we have written the weak QPO, and results are verified by structure function, PSD, wavelet, MHOV, and data folding. And in X-ray, this is a narrow line Seyfert-1 galaxy where we got a QPO using LSP WWZ method. And this result I will show gamma ray light curve where QPO is detected on the STV time scale using LSP WWZ. And here we got simultaneous optical and gamma ray QPO with 7.6 days period and 8 cycles. LSP, WWZ, and ARIES method is used. Here in gamma ray we got QPO in OJ287 with time scale of 314 days, and again the same method we use. Here again we got optical and gamma ray simultaneous QPO in 3C454 where QPO time scale is 47 days with 9 cycles, and we use LSP, WWZ, PSD, and ARIES. And a radio QPO in 3 bands we got in this Blazar AO0235 plus 16.4 where the QPO time scale is 665 days, and results are verified by LSP, WWZ, and PSD. So this is the typical light curve, and this appears structure function plot I showed. So this structure function plot motivated us to search for the QPO, and We got QPO by using MHOV, data folding, PSD, and wavelet. And we got 4.6 hours QPO, 3.8 cycles. And we explained this finding by using hotspot on accretion disk as well as the helical jet model. And we use this black hole mass estimation method formula. And we adopted these parameters and estimated the black hole mass to be 3.29 into 10 to the power 7 solar mass for non-rotating black hole and 2.09 into 10 to the power 8 solar mass for maximally rotating black hole. This is gamma ray light curve of another source. And you can see this is the full light curve, and we have just taken starting 6,000 seconds from here, and this portion is plotted here. And then we did this LSP. We got a 99.9% significance level, a peak here with period 71 days. And that is what verified by Redfit method and WWZ. So this Fermi data on B12, B20 plus 31, 17 days QPO. And here we have got the black hole mass 5.4 into 10 to the power 9 solar mass for non-rotating and 3.4 into 10 to the power 10 solar mass for rotating black hole. So now I will just summarize the result. Flux variability is shown in Blazars on diverse time scales using external Newton, Chandra, and new star data. In a single light curve of PKS 2155-304, we notice stable flux, QPO, decline flux, and flaring state. In long-term LTV light curve, optical and UV light curves were correlated, and soft and hard X-ray light curves were correlated.
So we have a few questions. The first question is that what is the origin of QPOs in Blazars? One of our audience want to know what is the origin of QPOs in Blazars.
Actually, basically QPO is still, if you see the standard Asian model, there is no model which predicts or which explains the QPO. So this is, I will say, very least understood property of AGN, because if you observe, you analyze hundreds of light curve and of a same source in same EM band, but there is a chance of detection of QPO either very rare or there is no chance. So actually we don't know what is the QPO, what is the origin of QPO, but QPO pattern you can see. This is the flux increase and decrease with the quasi-period in the way of quasi-periodicity. But so far you cannot say what is the origin of QPO, but as existing models are there, one can explain on 3 different models. IDV time scale, hotspot on accretion disk can explain QPO, or helical jet structure can explain QPO.
So there are different models for QPO. So there are more than one alternatives are there. Our next question is that am I audible?
Yeah.
So there are some guaranteed microcourses like GRS 1915 and GS29, which show both radio loud and radio quiet properties. And there's some emissions which are not like that. So why different emission phenomena are observed from same sources? The question is that why different emission phenomena observed from same sources? This is a question from one of the research scholars.
Pardon. Can you repeat the question?
Some of the sources shows both radio loud and radio quiet features. So why different emission phenomena are observed from the same sources? Probably it's with the accretion disk or something, accretion rate. Probably, yeah. So why different emission phenomena are observed from same sources?
So basically, these are either if you are talking about radio quiet and radio loud. So the fundamental difference is the radio emission. So radio loud object emit in radio, and radio quiet don't emit, or either if they emit very weak radio emission. So that's why if you see the narrow line Seyfert-1 galaxies and broadline radio galaxies. They show similar type of spectra, but they belong to two different classes. Is that okay?
Yeah. The last question is that what is if you can say a few words about jets? So what is the jets?
Pardon, jets. Actually,
jets.
Due to accretion, a lot of matter is trapped by the black hole, but there are some matter left which emit in the jet form with the relativistic speed.
Yeah.
Okay.
So those which are synchronous emission, those are actually jets.
Those are basically non-thermal radiation. Yeah.
Non-thermal radiation. So thanks a lot, Alok. Your talk was really marvelous, and we learned a lot from you. It was really beautiful things for us to have a scientist like you to be present with us. We are very much thankful.
It is my pleasure also to those students and colleagues. Okay, thanks.
Yeah, thanks a lot. So our next speaker is Somnath Nag.
Should I?
Yeah.
Should I stop presenting?
Yeah. You may. Yeah. Thanks. Just point to start with the So our next speaker is Somnath Nag. He's an eminent scientist. His work is in physics. So he works in the IIT BHU. So we are very happy to have Dr. Somnath Nag with us. So we will just check that whether Somnath, can you please start the PPT so that we can just check whether it's showing in the YouTube.
Okay.
Yeah. Because we are changing room from the from Professor Alok Gupta to EO. Operator, now, we will discuss the next room. Start করতে বলো, তুমি অনলাইন থাকো। Operator, please telecast the next room. Yeah, it's visible. Yeah. So, Somnath, probably we can start now. You are visible in YouTube.
Okay. And I will switch off my camera. I think that will save. Is it okay?
It's okay. Yeah, it's okay.
Okay. So then I am starting now.
Yeah, you just present your PowerPoint.
Okay, good afternoon to all of you. I think the slides are visible. Hello, are the slides visible properly?
I'm just testing, but yeah. Oh, yeah, it's visible.
Okay.
It's visible, yeah.
Okay, so good afternoon to all of you. And first of all, I would like to thank Dr. Sabyasachi Pal for inviting me to this webinar series. And I am also thankful to entire fraternity of Midnapore City College for organizing such a nice or taking such a nice initiative to organize this webinar series. So my topic would be evolution and interplay of nuclear shapes. And as the name suggests, so perhaps you must be guessing now that what about the shapes of a nucleus? So when we talk about nucleus, what first comes to our mind, that is, it has protons and neutrons inbuilt in it. But when we talk about the shapes, then it is some sort of bulk property. And I guess here we have a mixed audience. So I will try to keep my talk in such a way so that it is understandable for every one of you. And you are free to ask the questions at the end. I would love to reply. Okay, so let us look at the bulk properties of the nucleus in terms of different shapes. Let's proceed. Okay, so first of all, I come from IIT BHU. This is a map of Varanasi Hindu University, and this is the entire campus, and we exist as IIT BHU within this campus itself. Okay. Yes, so we are located somewhere here, and we have just completed 100 years of existence in 2019. So this stamp was released by Government of India. Okay, so now coming to the nuclear physics. Okay, so it has some broad divisions, you can say. So nuclear reactions, nuclear structure, where we will be focusing for today's talk. And then we have this high energy physics. Once upon a time, it used to be the part of nuclear physics, but now these two different fields have grown to such a large extent that high energy physics now forms a separate field as such. And among all these things, what is common is instrumentation. You need a very good state-of-the-art instrumentation to work on all these topics. Okay. So when we talk about nucleus, so it generally forms a vast laboratory which we can use to study many quantum phenomena, many electromagnetic phenomena. And while, as I told you, that instrumentation forms a major part, so it also helps you grow your knowledge in terms of electronics and other sort of state-of-art instruments. And nowadays, simulation also forms a large chunk of these fields. So it is a very important now that we simulate all the real life problems, and then we go for physical verification of those. Okay. Well, so let's start with brief history of this nuclear physics. I have just written down some of the major discoveries, and there are many more. So just I want to highlight why we are talking about these shapes. So if we just follow these years, so we can see that in 1896, okay, so discovery of radioactivity by Becquerel, and then gradually all of you know about these historical facts. What people may not be knowing much, that is in 1949, there was introduction to this shell model by Meyer and Jensen independently. And then in 1951, just 2 years later, this collective model of nuclear physics came into existence by Bohr, Mortensen, and Rainwater. And if we go by the Nobel Prize, then we can see, okay, so for nuclear physics, many people got Nobel Prizes. And interestingly, some of those prizes have been given in the field of chemistry, some have been given in the field of physics. But now if we come down to this Meyer and Jensen, we can see that for their discovery or for their proposal on this shell model, they got the Nobel Prize in 1963. And then if we move 1975, we can see Bohr, Mortensen, and Rainwater, these three shared the Nobel Prize of 1975 for proposing this collective model for a nucleus. Okay, so yeah, just before I proceed, I should just talk about the difference between these two. When we talk about the shell model, it is just like our electronic model. We have different energy levels with certain definite quantum numbers. We have protons, we have neutrons, we fill them one by one, and accordingly, we come out with the description of the various properties of a nucleus. But there is a problem. When we talk about a nucleus, so we can have okay, large number of neutrons and protons. And now if one sits and try to solve those equations, so it will be a huge gigantic equation. So okay, people do play with those equations, and nowadays you have very good computational facilities at most of the places. So people come up with the solutions of those equations, and they can describe the observed nuclear properties. Okay, but then at the same time, when we talk about this collective model, there we don't talk about single neutron and protons as such at the first sight. What we do, we combine the neutrons and protons, all the wave functions, and we talk about them as a bulk system. Okay, and interestingly, it was found that if you sit and do proper calculations with each individual neutron and protons and describe the nuclear properties, and instead you don't sit with those neutron and protons, rather you consider a bulk body like a sphere, like a prolet, like a oblate, and then do the dynamics, and you will be able to describe the nuclear properties as well. Okay, and there is a third rule also, so that is based on symmetry. If you know the symmetries properly, you can apply the rules regarding those symmetries, and again you will come up with the right results for the nuclear properties. Okay, so all these things get converged at certain point, right? And sometimes, okay, we do combine the shell model or individual particle model with these collective models, and that forms that forms the basis of some other model which we will be looking at. Okay, so just to quote this Gavor, so what he talked about, that though the investigation of different properties of nuclei, one thus is led to two widely different pictures of nuclear structure corresponding to the liquid drop model and to the shell model. That is what I was talking about. That shell model talks about individual contribution. When you talk about this liquid model, of course, liquid drop model, perhaps many of you have heard about this. So that is a bulk model. So these two are two different faces of the same coin. Okay. It is nevertheless not difficult to combine the most essential features of both models. That's what we are going to do in the due course of this talk. In the shell model, one regards the orbital motion of individual nucleons in the average nuclear field as the primary form of motion. In the liquid drop model, one looks at the simple collective motions of the nucleons. Okay, so that is the basic difference, and that is why these two get connected also. Yeah, last part I am not reading, so I have just taken this clip from literature. Okay, then he also do an analogy where he says that we can imagine a comet coming very close to our Earth. Principal effect of the passage of the comet would be that the rotation of the Earth would be slightly changed, partly by the oblate shape of the Earth and partly because of strong oceanic tidal wave that would be set in motion. Okay, so he tried to again correlate his model to whatever is known for the planetary motions. Okay, and I just got this figure from your internet, and I just put it here just to give you some feel that like we have these planets, Mercury, Venus, Earth, Mars, etc., and you can see they have a definite axis of rotation. And interestingly, if we, okay, all of us know that Earth's axis of rotation is not just vertical, it is little bit tilted at certain angle. Similarly for the Mars. For the Uranus, if you see, it is somewhat horizontal. And for Mercury and Jupiter, they are almost vertical. For Venus, it is oppositely aligned vertically. And Saturn, again, it is inclined. Okay. So this is a bigger picture, or this is a picture in the macroscopic world, which we all can feel, because for the nucleus, it is a quantum mechanical system, and no one of us can see it, can feel it, can hear to the noise of nucleus. So we need some picturization in our mind, to feel about the shapes of the nucleus. Okay, so from these planetary orientations, we can think about how the nuclear wave functions will be oriented in turn, and I will be showing you that how the nuclear shapes are aligned with different axes. The axis will be tilted, axis will be oriented in some other direction, and how you get the distributions. Okay. Well, now again, so we are talking about nuclear shapes, but before nuclear physics, we talk about atomic physics basically. So why not in atomic physics we talk about different shapes? Of course, with the molecules we talk about different shapes, but I think those are not as explicit as the nuclear one. So first, let's come to the atomic one. So in the atomic case, we know that there is dominance of this 1/r type of potential, and that basically would be giving you some sort of spherical distribution. Okay. On the other hand, when we talk about the nuclear system, we have some average potential. It can be a square well, it can be something like harmonic oscillator. There are some specific potentials like Wood section. You can club other interactions with these average potentials, so on and so forth. And because of all this, we generally tend to get various types of shapes for a given nucleus. So here I have just put up certain cartoons. You can see the brown colored one is somewhat spherical. Then you have this green colored oblate. This light sky color, it is prolate. The below green colored, you can compare it with the top green colored body. So below what I have shown, that is little bit more extended. So that is why it is being called as oblate super deformed. Similarly, this bluish body, so you can see it is very largely elongated. So that is why it is being called as prolate super deformed. And further elongation is there, so you call it as hyperdeformed prolate. And then you can also have something like this thing called pear shaped or like banana shaped. So these all are different shapes, or maybe shapes of the distributions with which we can observe our nuclei. Okay, now, okay, so let us try to formulate it mathematically. So when we talk about these different shapes, the easiest way to consider is to consider the axially symmetric nuclei. Okay, so there is an axis of symmetry about which the distribution is oriented. Okay, now when we talk about a sphere, so sphere is non-deformed one, but if we talk about oblate, if we talk about prolate, those are what? Those are basically some sort of deformation beyond the spherical shape. So if we deform the spherical shape, we can get prolate. If we deform the spherical shape, we can get oblate. Okay, and if we can deform it in some other way, so we can get triaxial also. Okay, so that means somewhere my radial coordinate would get changed. So let me write this modified r as r function of theta and phi equal to r0, and then I have this expansion 1 plus summation over some coefficient. Then you have spherical harmonics. These are defined with these parameters lambda and mu. Lambda basically gives you the order of the mode, like monopole, dipole, quadrupole, octupole, and so on. So lambda 0 corresponds to monopole, lambda 1 corresponds to dipole, lambda 2 corresponds to quadrupole, and so on and so forth. And across each lambda, we'll be having again projections from projections mu, which will be varying from minus lambda to plus lambda. Okay, well, it is very much well known that if you talk about the monopole or if you talk about the dipole, then it generally doesn't add any new physics to the existing nuclear body. Once we go to the quadrupole, that is the first point from where some new physical aspects are being added to the nuclear system. So generally we start with the quadruple systems in itself. Okay. So when we start with the quadruple system, so that means we need to start with lambda equal to 2. And we are talking about some sort of axially symmetric system. So there we'll lose some of the mu, some of the projections will be gone because of the symmetry. And ultimately for those type of quadruple systems, we are left with only two parameters. One is alpha 2, 0 and another is alpha 2. Okay. Otherwise for lambda equal to 2, we should have mu equal to -2, -1, 0, 1 and 2, 5 parameters. So but because of the symmetry, so some of the parameters will be gone and we will be left with just 2 parameters. And then what people did, people reduced it in form of thing, beta cos gamma and 2 as 1 by root 2 beta sine gamma. There is some advantage of this nomenclature. And if you just remember your maybe class 11 geometric classes, or maybe now class 9 or 10, so it simply resembles your r cos theta and r sin theta term, and immediately you will realize that, okay, if we define it in this way, later on we can define a mesh which will be forming some sort of circular distribution, and along that we can move and look for the deformation where my nucleus is located. Okay. So with this nomenclature and all, so what we can look for? We can look for the change in this radial coordinate due to the deformation beyond the spherical shape. So if we look for this change, so that is being shown as delta rk, k being equal to 1, 2 and 3 for x, y and z axis. And okay, it comes as some constant beta cos of this argument gamma minus 2 pi by 3 k. Okay, so here let me tell you, this beta actually signifies the axial deformation. So like if we are talking about trolley, that means we are pulling the top or bottom of a spherical object and extending it, okay, or stretching it. So that stretch is being shown by beta. Or if it is oblate, we will be pressing it so that it becomes oblate from a spherical shape. So whenever we will press it, so that compression, so that delta is given by beta. Okay, and the gamma is actually called triaxiality parameter. It is a bit difficult to picturize in mind, but you can just understand it in that way, that whenever we wash our clothes and then we go for drying it up, so what we do, we generally twist it. We hold both the ends of our cloth and then we twist it. We give two opposite torques, you can say, and we twist the whole thing. So that twisting effect is being parameterized by this gamma. I will show you some animations. Hope we will get it from there. Now here we have a very important graph where it shows that x-axis is gamma, the y-axis it has some parameters varying from -1 to +1. Okay. Now if you see, there are actually 3 curves. Okay, and each of these curves are being represented as z-axis equal to 3, y-axis k equal to 2, x-axis k equal to 1. Okay, so for your convenience, I will just stick myself to one value. Like let me stick myself to gamma equal to 0. If I go to gamma equal to 0, what I find? I find that my x and my y are converging at the same point. That means axis of the nucleus along x and y are now same, whereas z is in the positive direction. Fine. So the shape is like this. Okay. Now if I go to 60, here you can see that x and z, they are same, but my y is you can say elongated or compressed, whatever you say. So it is in -1 direction. Okay, so you can see this shape. So likewise, if you just keep on putting your k equal to 1, 2 and 3 and keep on varying your gamma, ultimately you will see you will be getting prolate and oblate shapes with different orientations. Okay, and that is what actually Lund observed, and he came up with this Lund convention. You can see this dimensional plot, and here you can see these circular rings, and now you can correlate this thing with this beta cos gamma and beta sin gamma nomenclature, which I just now explained to you. So here you can see this yellow colored line is gamma equal to 0, which I explained just now. So here gamma equal to 0, it will be just like a plate. Okay. If you go to gamma equal to 60, you can see here it will be just a oblate. You can go to the negative gamma also, minus 60, minus 90, minus 120, and accordingly we will be either getting prolate or oblate. But what is important, you can concentrate on the direction of these axes. So gamma equal to 0, you see it is a prolate and the axis is vertical. It is not along the symmetric axis. Okay. Here another important point is there, that is, if we are talking in terms of quantum mechanical system, we are talking about a rotation, and my rotational axis is oriented along the symmetry axis of the body. Then should we observe rotation? Of course not, because if symmetry axis and rotational axis coincide, whatever rotation will occur, we won't be able to distinguish between the different phases of the body. So always we need to have the rotational axis to be perpendicular to the symmetry axis. So that is what being shown here. Okay. For the oblate, you see rotational axis and symmetry axis have coincided at gamma equal to 60. So that means here this rotation will stop. You won't be distinguishing between the different phases of the oblate shape, and we would say that rotation has stopped. Okay. Similarly, if you go to gamma equal to minus 60, this is oblate, but just mind it that here the axis is not along the symmetry axis of the oblate, it is along the perpendicular axis to the symmetry axis. So that means here we will be observing the rotation of the oblate body. Okay. So similarly, if we just traverse throughout this mesh of beta gamma plane, we will be getting different shapes in terms of plate and oblate. And for your recap, I would say that it is just for the quadruple shapes. Okay. So hope all of you have understood about these shape parameters. Okay. So now let us go to some real life examples. And here you can see my animations are here, so which I have taken from this website. Long ago, it was done by some master student in Lund University, Sweden. So here you can see this beta equal to 0.3 vibration. You see this vibration is some sort of oscillation about this spherical shape, and since beta equal to 0.3, this defect or this deformation is not very large. Go to beta equal to 1, now you see how much stretching is being shown here. So it is a lot more. Okay. So, and the last plot is for that gamma. So maybe you can get that feel that I was talking about that twist. Okay, so that twist at both the ends. So that is basically by how much angle that twist has been applied. So that gives the gamma. Okay. So this beta is directly observable, observed in the experiments, but the gamma we actually extract it out from some model. Okay. Okay. So here is some level scheme. Level scheme means we have, these are all gamma rays, whatever arrows you can see. These gamma rays are basically connecting different levels within a nucleus. Here the nucleus happens to be 120T. And now I would suggest to concentrate at the energies of these gammas. So this is 560 kV. These energies are in the order of, in the units of kV. So this is 560. Next one is 601. The next one is 614. After that you see a comprehensive jump. It is 876. But again, they stay together. Okay. So what is happening? If we talk about some harmonic oscillator potential in quantum mechanics, we have n equal to 0, 1, 2, 3, these levels. So we have this energy equation like equal to n plus 3 by h cross omega for three-dimensional harmonic oscillator. And if we keep on varying n as 0, 1, 2, 3, 4, and so on, so we'll be getting energies of these levels. But what is important is the difference between the energies of two consecutive levels always remain to be the same, right? So that happens to be h cross omega. Okay. Now we are looking at some observed data. So here we are getting these transitions or this delta in energy in quite similar in terms of quantitative values. And from here we can guess that, okay, my nucleus is undergoing some sort of harmonic oscillator sort of motion. And because of that, that thing is being replicated in experimental result. Okay. Of course, for the nucleus, it is not very much simple as n plus 3 by h cross omega, like three-dimensional harmonic oscillator. Rather, it is n plus 5 by 2, some sort of five-dimensional system, h cross omega. And okay, so here we have defined two omegas. So one is omega beta, that is angular frequency for the beta deformation, another for the gamma deformation. And we have then sort of these coefficients. One is simply like your three-dimensional harmonic oscillator. The difference is that it gives now five-dimensional thing. There are other parameters. And for the gamma one, it comes out to be like this. I am not going into these details. That demands discussion on something else also. So, but you just take it, you can feel that, okay, this gives some sort of oscillations. Okay. Well, so these spectra generally form the vibrational spectra, and from here we can conclude that, okay, my nucleus will be vibrating, and this type of vibrational effect is observed mostly at low and medium angular momentum states. If you go to a very high angular momentum, so then mostly rotation will predominate and vibration actually collapses. Next. Okay, now one interesting fact, sorry, here this E, I missed this E. So this is 120 tellurium level scheme. This is 121 tellurium level scheme. What is the difference between 120 and 121? We just have only one nucleon extra. So that is the neutron, because both are tellurium, so Z number is same. And here what we see, interestingly, that, okay, this one I have already explained. Now if you see these things, this 121 tellurium level scheme, here I have 631 kV, then 728 kV, then 677 kV. After that it increased by a large margin. So below what you see, that is, these are again lying to some similar, these are having similar values. And interestingly, what is the difference between these two? That is, we are having one extra neutron. Then what we can do, we can look for that where my neutron will sit if we talk about in terms of shell model. So obviously in this, you just take it for granted now that in this mass region, this extra neutron will go to the H11 half orbit. Okay. Now if you know the energy of single particle energy of H11 half, so then what you can do, you can basically couple this one with this vibrational core of 120, immediately will be generating all this. Okay, so that means here you see we talked about the vibrational model, which is the collective model, and then immediately if you have some odd neighbor or odd nucleon neighbor, so there you can apply the single particle, or you can merge the single particle formalism with the collective formalism, and with that you can describe the level scheme of that odd mass nucleus. Okay, so here both of them are coming together. Okay. Okay, so this is, I think, who are doing masters, they might be acquainted with. These are nothing. Okay, let me just go back to my last slide. Okay, so when we talk about these transitions in terms of which are coming out of a vibrating nucleus, so what we see that These are in terms of transition of phonons. Okay, just like we have photons for these optical rays, here for the vibrations we define this lowest unit as phonon. So since we are talking about quadrupole system, so we'll be having quadrupole phonons over here. Okay, so that means when I have 2 to 0, so 2 is the spin of this state, 0 is the spin of the ground state. So 2 to 0 transition is there. That means we are having a quadrupole phonon of lambda equal to 2 order. Now for the next one, what is happening? For 4 to 2, again another quadrupole phonon with lambda equal to 2 is being emitted. Now if I want to reach from 0 to 4, that means I need to couple one quadrupole phonon with the other quadrupole phonon, means 2 quadrupole phonons are being coupled. If I want to go from 0 to 6, so then I need to couple 3 quadrupole phonons. Okay, and like that you move on, you need to couple more and more quadrupole phonons with lambda equal to 2. That is what being shown here, like lambda equal to 2 are there. This is some sort of coupling scheme. Again, it is part of classroom teaching, so I am not going into the details. But if you just couple 3 of the quadrupole phonons, you will be generating angular momenta of the order of 6, 4, 2, 3. Oh, sorry, I think it has gone below anyway. So you'll be generating these many angular momentum. Similarly, if you couple here, I don't know, some problem with the sharing. Here 4 to 0, 3J value should have come. So leave it and let's go to the pictorial representation. So here you can see I have 0. 0 to 2, I only have one quadrupole phonon. So it's simply 0, next I have 2. But then to next 4, I need to couple 2 quadrupole phonons. But coupling 2 quadrupole phonons would fetch me 3 states, 3 J states. That is 0, 2, and 4. That is what being shown here. So whatever we see in our experiment, 0 state, 2 state, 4 state, 4 state is actually part of this 0, 2, and 4 combination, which is being generated by coupling of 2 quadrupole phonons, right? If now I couple 3, which I have shown in my earlier slide, we will be getting 6, 4, 3, 2, and 0. These many states can be generated. So my observed spin state equal to 6 is a part of this 3 quadrupole phonon coupling. Okay. Others will go to something else, which just I will just be explaining to you. Okay. Then if you combine 4 of them, you'll get so many of these J states. So 8 will just pick up for our vibrational states. Okay. So 0, 2, 4, 6, 8, but they do have other states also. Okay. Now see, they have bifurcated or they have divided all these states separately. So you see 0, 2, 4, 6, 8. This one they will be calling as ground state band. Fine. Next you pick up these 2, 3, 4, 5, 6. Okay. So this will be forming something that is gamma band. I'm coming to it. Then you have another 0. This 0 of the quadrupole phonon. 0, 2, and 4. So that will be beta band. Again another 0, 2, another beta band, and so on and so forth. Okay, so what about this beta band and gamma bands? That is because beta band will be built on these beta vibrations when you have this elongation or compression about the spherical body. Okay, and the gamma system or the gamma band will be formed over this gamma twisting. Okay. But okay, again, we can do the calculations, quantum mechanical calculations can be done, and we can very easily see that the starting point of this gamma band will always be 2 units of spin. Don't start at 0. Okay. So having said that, next let's go to one of our works in 123 xenon. Here again, I am showing you some combination of gamma rays. We have some bands. These are 4 band numbered as 4, then this is band numbered as 5, this is band numbered as 9, 10, 11, 14, and 15. And then what we observed is band 4 and 5 in this 123 xenon were formed at some gamma equal to 20 to in between 20 to 25 degree. And what was concluded that they are coming from this gamma vibrational band of the even core, meaning you just consider maybe 124 xenon or 122 xenon rather. So that is the even core, and if you have this gamma vibrational band, is that extra particle which is getting coupled with this, as I have shown you the example with 121 tellurium and 120 tellurium. So that was coupling for the beta. Here we have observed coupling for the gamma band. Okay. Okay. Here we have shown some figure where you can see the y-axis is spin, x-axis is simply E gamma. Okay. And then here these are different bands. 1, 2, 3, 4. This is band 1, band 2, band 3, 4, 5, 6. This is what nomenclature we have followed here. So then for these bands with different gamma, so I have just shown you a part of the entire level scheme. It's not the complete one. So if you just plot it, these spins with E gamma, so what we see that this type of distribution is being observed, and we can search for band 4 and 5 over here. So band 4 and 5 are being shown as these red colored squares. So here are these band 4 and 5. Okay, and they get connected 9 and 10. So 9 and 10 are here. And here something interesting has happened. This band 9 and 10, you can see they are going like this, with spin is varying with E gamma in a linear way. Then suddenly at around 1 MeV, there is a jump. Okay, so the jump has been shown with these black colored straight lines. And after this jump, now they are again following a straight line after this jump. So this jump, if you observe in terms of the spin, maybe you can check it over here. It will be somewhere between 23.5 to 41.5 or so. Maybe some 8 H bar of spin, spin gain in spin, or somewhat like that. Okay, so a huge gain in spin one can observe. So this type of phenomena we have observed earlier in cesium nuclei. So there I will explain what is the cause of this, and this has something to do with the shape of the nucleus. Okay. So having defined this beta vibration and gamma vibrations, so just a pictorial representation. So whenever we talk about the spherical body, like just you make a bubble out of soap film, so immediately you leave it in air, it will form a spherical bubble. Okay, so always these spherical systems are lower in energy or favorable in energy. Okay, so all of us know about the magic number nuclei, which are stable in terms of energy, and that then what we observe is within the magic number nuclei, we generally observe spherical shapes. Okay, and these magic number nuclei are very difficult to excite because they are already stable, and you can observe from 0 to 2 you have such a huge difference. Okay, next we keep on moving. If we move towards this mid shell, so we see that this deformation is being introduced, it is getting deformed. You go to the actual mid shell, again it is completely deformed. After crossing the mid shell, when we head for the next magic number, then again the story is repeated, and at the next magic number, again the nucleus become spherical. Okay, and when we talk about this vibrational model, because our difference between the two levels are always same, that is, if I am talking about the energy of the 4 H bar spin, so it will be just twice of the 2 H bar spin, right? So because these are all the differences are same, so that is what being shown here. The ratio of 4 to 2 state comes out to be 2 for the vibrational one. For the magic, the spherical one, it is below 2, and in between, when you go to the mid shell where the nucleus is completely deformed, then it undergoes mostly rotation. From the ground state onward, you will be having the rotation. This equidistant levels won't be observed anymore, and there this 4:2 ratio comes out to be 3.33. So let me go to the rotational model, then you will be getting it. Okay, so before the rotational model, since we talked about this beta and gamma parameters, so here there is something for you. Just concentrate on this. Here beta 2 and that beta both are same. So different symbols are being used. So here you just consider it as beta. So that beta equal to 0 if you just read this line, this vertical line. So this is nothing but whatever we read about the shell model in our textbook. Zero deformation shell model. G9 half, D5 half, G7 half, S half, H11 half, D3 half, so on. Okay. But interestingly, as soon as we introduce this beta deformation parameter, you see immediately one level, let's say G9 half, gets separated into different sub-levels. So one is 9/2, another is 7/2, then 5/2, 3/2, and half. So all are your MJ values basically. Okay, so what we used to study about this angular momentum, L and then ML values. So it is simply like that. You have the J value as 9/2, and then the deformation actually breaks the symmetry over here and or degeneracy over here. And because of that, we get these subshells out here. Okay. So with deformation, we'll be having different subshells. And interestingly, if you observe closely, you can see like here, D5 half, it is steeply coming down, and G9 half, 9 half subshell, it is going up. So that means if there is a nucleus which exists with theta value 0.3, so there, after filling up G9 half up to 7/2 sublevel, will fill up D5 half's half level. Okay, then G9 half 9 level will come. Okay, so that means my Fermi level would keep on changing with the introduction of the deformation. Another interesting fact is that on this side, you can see the deformation is positive. That means we are having positive stretching. Expansion is there. So that is, it leads to the plate shape. On the other side, left-hand side, we see the negative values of beta. So that means there is compression. So it will be leading to the oblate shapes. And what you can observe here, if you observe closely, the energetically, what you call this benchmark of energetically favorable orbitals or the sublevels in the plate side is just the opposite that of the oblate side. Okay, so here you can see this bottom line of the 5 half sublevel is 5/2, whereas the bottom shell is on the prolate side, it is half, and the highermost one will be 5/2, whereas here highermost one will be the half. So oblate and prolate, they are, you can say they are a bulk system, but if you look at the microscopic level, so if you talk in terms of the shell model or the orbitals or the sublevels, so then we see that those get affected because of these bulk properties. Okay, so let's move on. Yeah, this is just the explanation of the same thing which I was showing you. So here there is a nice picture with this prolate and the oblate, and here you can see these single particle orbitals or the subshells have been shown as J1, J2, J3, J4. So from here you can get an idea. You see here there is the plate aligned with the symmetric axis along the horizontal one, and you have J1, J2, J3, J4. So here this J4, it is aligned with the maximum matter. So matter is maximally aligned along this direction. So J4 is aligned with this. Whereas for the oblate one, you see here there is the least amount of matter, whereas J1 is aligned with maximum matter. Okay, so this is the reason why we get this type of flipping of orbitals in terms of energy in case of prolate as well as in case of oblate. See here they have shown it schematically. So these are all the projections. So omega 1, 2, 3, 4, and here it starts as 4, 3, 2, 1. This is oblate side, this is prolate. Okay. So this is the effect we have on the orbitals. Okay, now coming to the rotation. Okay, just wait. So rotation, very initially while talking about the Lewis convention, I told you that when we talk about quantum mechanical system, rotation should always be along, rotational axis should always exist along the perpendicular direction to that of the symmetry axis. Okay, so here some again animations have been shown. This is spherical nucleus, so spherical nucleus should not be showing rotation at all. Okay, because it is sphere, totally symmetric. Oblate, here you see it is rotating along the vertical axis. Since we have these white colored lines, that is why we are able to recognize that rotation is taking place. If it would have been simply red throughout, we would not have realized it. Okay. Similarly, this is prolate and rotation is along the symmetric axis. So we won't be distinguishing this rotation. So what happens in nucleus, that when we keep on pumping in more and more energy, more and more angular momentum through excitation, that nucleus keeps on rotating, okay, along an axis perpendicular to the symmetry axis. But while rotating, what will happen? All these nucleons within the orbitals will get aligned along the rotational axis, and at certain point of time, this rotational axis will coincide with the symmetry axis, and the rotation will stop. Further, you need to generate rotation, then you need to break the core, excite more and more nucleons from within the core, and then they will again try to get aligned with the rotation. You will generate more rotation, and that rotation will get terminated at some point of time. And whenever there is rotation, you will be getting this type of smooth band structure. And very simply, because rotation is there, you can just try to look with this relation. You can look for the state's energy, whether it is varying as quadratic function of this angular momentum. So you can just plot it, excitation energy versus spin. You will see some sort of parabolic curve. You can also plot it with I into I plus 1, so that will be more or less straight line. There are some fluctuations, so we don't see it exactly straight line at the lower end. Okay, so with this we can check, like if we have equidistant or equispaced levels, we can talk about vibrational states. If we have this type of rigid rotor equations getting verified, we can say that there is rotational motion. But of course, this moment of inertia, it may not be matching with rigid rotor moment of inertia because there is deformation, so it gets changed. Okay. These are some observed results from 122T tellurium. Earlier I showed you from 120 tellurium, and now here you have 122 tellurium. You can see these all gamma ray bands, very smooth bands like eye structures all throughout. And what is interesting, that is we can plot this spin again with E gamma, as I have shown you in one of the last slides. And E gamma, so just take care that E gamma is the transition delta energy between two states. So you'll have to sit and just calculate it for E for say J state and E for J plus 2 state. You calculate it, you will see that it will give a linear function with respect to the spin, and you can see such a nice linear plots are being generated for these bands. So if one can do it, so immediately one can extract that rotational motion is taking place within the nucleus. And these are from some other literatures like 125 xenon and 126 xenon, etc. So here what you can see, again, very nice linear plot is there. But for this 125, the star marked curve, one can see around 1.8. Again, there is little bit of notch is there, and then again it follows a straight line. So I explained it in case of 123 xenon. So this type of phenomena are being observed. So there are two different reasons. One is that the nucleus is following this configuration throughout up to this. After that, suddenly some other configuration becomes stable in energy, and then that configuration is being followed. So this changeover in the configuration is being replicated as the delta change in spin. Okay, and the newly found effect that we reported in cesium and again that xenon, 123 xenon, that it is not change in the configuration, rather it is change in the shape of the same configuration that can also give you similar result. So just looking at this change, we can't tell, we need to probe in further. So I'll show you one example with that one. Okay, so now coming to that same nucleus, those long bands. So we did some theoretical model calculations. These calculations were done with some model called Crank-Nielsen-Stutinsky model, where we take care of the collective phenomena as well as we can define the each individual occupancy of the orbitals. So somehow it is macroscopic, microscopic model, right? So now these plots are being shown. So what are these plots? So y-axis, you see it is something epsilon 2 sine gamma plus 30 degree. Let's talk about gamma. X-axis is epsilon 2 cos gamma. And again, you can now correlate it. It is just like r sine theta and r cos theta. You plot it over a plane, so you'll be getting some circles. You can see these dotted circles are there, nicely placed dotted circles are there. And this epsilon 2 is basically that axial deformation parameter. It is proportional to beta. Gamma is gamma. And plus 30 because we have shifted our origin from the horizontal axis to this tilted axis. Okay, now let's understand these plots. These are called potential energy surface plots. And the color code basically gives us the stabilization in energy. For example, wherever we have this deep blue colored minima, we understand there the energy minimization has taken place. The energy is minimized at this point. And since energy has been minimized, the nucleus is likely to stay highest probability within this deformation range. Okay, so like here we have this this blue colored minima. So here the deformation, still deformation is 0.2, and my gamma value is around gamma equal to 0. Okay, so my nucleus will be having the deformation parameters as 0.2 and gamma equal to 0. And what was my gamma equal to 0 shape? That was prolet. I explained it initially with the Lund convention. So maybe you may not be remembering it, but now you can correlate it. So here in 32, the nucleus is having prolet shape. Then at 36, we can now keep on tracing this minima, and then we can say that how the shape is getting changed with the change in angular momentum or spin. So then at 36, it remains there, but you see that the deformation has decreased a little bit. Gamma 40, it is quite interesting. You see, at the same point of time, we can have one shape here, below 0.2, gamma 0. Another shape at around 0.3 beta, gamma, I think, in between 0 to 15 degree. And then here a small minima is being generated, that is around 0.4, very highly deformed state. And here the gamma is around 30 degree. Around 30 degree, these are basically triaxial. And so you can see, so prolet with different deformation, axial deformation parameters, and then we can have the triaxial also. Okay, and then 44, you see again these shapes have somehow vanished, you can say, and only this middle shape, it exists here. And you keep on going at around 52, you see some new minima has generated here. And so what we can guess from this plots, if we keep on guessing, we can guess that as we are moving along the angular momentum, we are pumping in more and more angular momentum to the nucleus. So the shape is getting changed gradually. At the same point of time, at the same spin, there can be two shapes, they can coexist, and you can have two different bands over here. So next, what is our task? That, okay, we have figured out which minimum deformation states are there, which are energetically favorable, but we are talking about nuclear physics. So we need to know about the orbitals where my neutrons, protons are distributed. So that thing, because this model is macroscopic come microscopic, so then we actually look for this minima, probe into this, and we try to look into the fact that which sort of nuclear configurations, which sort of distribution of neutrons or protons in whatever orbitals will be giving me this kind of shapes. Okay, so this probing have been done in these two plots. I am not going into details of nomenclature because verbally, if I tell, I think it is hard to understand, but you just understand it like that. These different symbols, different colors are giving me different distributions of neutrons and protons. And here y-axis is my energy. Okay, energy beyond some reference code. So again, I am not going into the details. Basically, it is the stable even code, and we are looking for the excess energy with the valence nucleons as a function of the spin states. Okay, so if we do it, so we can get so many of them. You can see these are all low-lying energetically favorable configurations, and some of them would fit into our experimental observations. Okay, well, so yeah, I was talking about this rotation. So rotation goes on. So will it go on forever? Of course not. Here is again another cartoon. So this one can see. Okay, just let's wait. It will stop. So basically, you can see this is a core, even core. We have two valence nucleons, green colored dot balls. Okay, and we have this rotational axis. Okay, perpendicular. So now you see they have this has started to rotate. As this angular momentum will increase, the alignment of these nucleons will get gradually increased along the rotational axis. Even if you don't understand this cartoon, you can just remember your childish play. We used to tie up a stone with a thread, and then we used to rotate it on top of our head. So when you used to start the rotation, so when the rotation speed was low, then what shape it used to have? That thread and stone system used to form a conical shape. And as we keep on increasing our speed, it used to get flattened, and ultimately it would have made a equatorial plane. Okay, so it is just the same thing, and beyond that, if you go, it will just fly off. Okay, so here also, if you keep on pumping in energy and angular momentum, it will go to like this. That rotation will stop after maximum alignment, and beyond that, if you keep on pumping and pumping, after that fission will occur. Okay, so it will break away. Here are some pictorial representations that if you have one pair, so it will keep on aligning. When the maximum alignment is done, that rotation is stopped. Next, we break up another pair, this blue colored one, go on to breaking up the pairs in the valence shell. And once the valence shell is consumed, after that one can excite it from within the core. So this phenomena is basically called this band termination. And here I have again shown, you can say a cartoon or animation for the calculation. Again, this is that same potential energy surface plot. It actually goes with this one. So when it will stop, it will actually go to this 60, where the rotation will stop. Okay. I think this level scheme actually I like very much, because here this type of rotational motion has been observed. And what is happening, you can see this type of flat structure. Here you see there is a nice smooth rotational structure, or band structure rather. Then there is a flat portion, above which you don't see that much smooth band structure. But again, some small band here and here it is generated. Again, it stops here. You see again a flat roof of like structure is there. After that, we have only one single particle sort of conditions. Okay, so if one if one sits and calculate these configurations with valence particles, so one can generate this much angular momentum with certain pair breaking. You break further pairs, you will get up to 55 by 2. You break the ultimate pair, you will get up here. Okay. No, here and then 55 by 2 up here. After that, we don't have any band. Okay. So from here, just by looking at the level scheme, this distribution of gamma, one can say that where it would stop. Yeah, so here again I have shown for 120 tellurium, this type of band termination has been observed there. Let me just show you the energy plot. So again, this is that energy scale with respect to some reference code with spin, and here we have compared this for the tellurium 114 to 122. We have different Newton numbers over here. And what we can see at around 16 plus, this gets minimum. Getting minimum in energy means these are getting stabilized. When it will get stabilized? When all the pairs will be aligned. Okay, aligned or either fully aligned or partially aligned. So like 116, it corresponds, sorry, this green colored triangle, it corresponds to 118. And you see for others, it is just above this. So from 114, if you start, 14, then 16, then 18 stable, and again comes back 20, and then 22. Similarly, for the 22, when all the pairs are broken up within that valence space, so then again we see this type of nicely dropping in energy as a function of spin. Okay, so what happens now? What about the shape then? So as I told you that if it starts with the prolet, at the termination it should be having the oblate shape but rotating along the symmetry axis. Only then that rotation will stop. You will see this type of termination. So this has been again shown here as pictured. So here you can see some oblate shapes have been shown here, and beyond this we can again have further gamma band we can generate, but that can only be generated through the further excitation from within the core. But again, you will be having the plate shape even after attaining the oblate one. This is one very celebrated figure from this 158 paper, RBM paper. So this we always refer to everyone. So here you can see this downstate band, violet colored, then neutron alignment, then proton alignment. It is going on like this. Then you see there is nicely dropping in states, and here they have shown it as oblate one, and terminating state they have represented it. Above you can see a green colored structure is coming in. So this will be generated through the further excitation from within the core. So again you have the prolet one. Okay, so this prolet and oblate, these stories in between that 124 cesium. This is what I was telling you. Again, here we were analyzing this gain in spin or gain in alignment. So spin versus E gamma plot is being shown here. And here one can see that band 3, band 4, and then band 2, band 1, it was not observed up to the highest, I guess. But for all others, this difference is around 8 H-bar. Okay, so we sat with our calculations and tried to see that, okay, whatever neutron and proton distributions are there, whether with that we can define or we can explain this gain in spin. But we didn't succeed. Later on, it happened that in 124 cesium, again, if we look for these potential energy surfaces, we have so many shapes over here. You can see lot many shapes are existing all together at different spins. And here if you just see here we have marked this minima as 1, 2, and 3. Let me go to the next page. Here are some calculated configurations, and each configuration we try to look into different minima. Okay, and then we realized that this 8 bar of spin alignment can't be simply discussed in terms of particle alignments. Rather, we need to take into account the shape change of a particular configuration. So that is why one can see here, these are all configurations. So one configuration, this 4165, that has been shown within 2, and then within the minima 2 and also within the minima 1. Okay, so within 1 and 2 we have shown these two, and because of that you see there are huge differences in the this excitation energy versus spin plot, and this changeover would be explaining us that extraordinary gain in alignment. These two plots I am not explaining, but here actually one can sit and do further more calculations and see that the spin contributions coming from individual orbitals at a given deformation would keep on changing with the deformation itself. Okay, okay, for neutrons and protons I have shown it for the same deformation. I had another pair of plots which I have not included it here, but here also you can see for the neutrons and protons there is huge difference between the alignment of the orbitals. If you just see the spin contribution with respect to the observed angular momentum of the nuclei. Okay, so till now we are talking about quadrupole deformed nuclei with axial symmetry. Now, what about the triaxial nuclei? Okay, so with this I will be ending my talk. The only 3 or 4 slides are there because these are quite hot topics nowadays. So whenever we go for this triaxial nuclei, there are 2 signatures. One is called chirality, another is Ubling. Let's look at it. So chirality in the nuclei, if we talk about, I think all of us understand the chirality, in terms of chemistry, where we have different distributions of these atoms within the molecule. And the chiral, when we talk about the chirality, the most I think prominent example we talk about that is of our palm. And but what is the chirality? What remains invariant? So those are basically spatial chiralities. We are talking about something which are defined in space coordinates. Okay, but in case of nucleus, so it's not the space coordinate. Here let us have a quick look. So here is a nuclear core. I have proton angular momentum being shown as J pi. I have neutron angular momentum being shown as J nu. Both are aligned at mutually perpendicular direction. Okay, so maybe along the short and long axis. And then I have one total angular momentum of entire core that is being shown as R. It is along the third mutually perpendicular axis. The resultant is J. Okay, total angular momentum. Sorry. So total angular momentum. Similarly, so this distribution can be flipped off. If we flip it off, J pi remains same, J nu remains same, R gets flipped on the negative, rather it is from negative to positive, and J is along this direction. Okay, so these two structures will form counterparts of the same event, you can say. One is right-handed, another is left-handed, but here we are talking in terms of angular momentum. Okay, so basically these are in time reversal. We can say these are time reversal chirality. And what is the signature? Because ultimately whenever we will be performing the experiments, we will be only having the gamma rays. So the signature is that we will be getting one pair of bands, like here it has been shown, band A and band B. What is good about these bands? Band A, if you look at the spins and the energy of the levels, these are almost similar to the band B spins and energy of the levels. And rather, this band B and band A are also talking in between each other. Okay, so In general, we will be having this delta I equal to 1 bands of the same parity. The parities are same. Very small energy separation. They are very similar in electromagnetic transition rates. And so if this type of bands are observed, so we can go for the conclusion that chiral nucleus is behaving as chiral and it is having a triaxial shape. Okay. And the next counterpart is the oblong. So here also, when we talk about Bohr, so actually Bohr Mortensen, they have suggested for this simple oblong. So when we do not consider this angular momentum from individual particles, so here simple oblong graph A, you can see. So these three axes are there, long, short, and medium. And we have this coarse angular momentum, which happens to be the J here, and it oggles like the precision of a top, it actually precises about this axis. Okay, so this has been suggested by Bohr and Mortensen, but as far as I know, this has not been observed experimentally till date. What has been observed, that is something else, and we have the contribution from the individual particle. So if you just look at this B, at the B figure, so here we can see that this is the medium axis. This R is now aligned along the short axis. J is somewhere in between, and then we have the capital J, resultant of this two. Then this oblique motion can be longitudinal and transverse. So you can see in one case, this individual J, it is aligned along the medium axis. Another case, it is aligned along the short axis. And accordingly, there will be this precision, different sort of precision. There are different signatures of the how to look at this problem, and one can observe. So in recent times, from Notre Dame University, this type of observations have been made. Even from India, two works have been reported very recently from VCC and one from BHU Physics Department. So where they have observed this type of motion. So this type of theory has been given in, I think, year 2016, and the observation has been made in 2019, 2020, and now many more reports are being published with this type of motion. Yeah, here I have shown how to look for this, but I think I can skip for time being. I have explained the phenomena. This is what being done. Before I close in, till now I have talked about what sort of shapes a nucleus can have, what the shapes can do to your orbitals or to the alignment of the particles, and how the angular momentum and excitation energy would see different shapes, coexistence of shapes, and so on and so forth. But ultimately, what we had at our disposal, we only had the gamma rays. So just one needs to understand that whenever we perform one nuclear experiment, basically we have the energy information of the gamma ray, which is coming out from the excited nucleus. Then we have the information of the intensity, how many counts have come in. And if we are talking about a 4 pi directional detector system, then we have the information of the angle theta and how the intensity is varying with theta. Only this much. We don't have anything else which we can observe. But then we need to play with this energy, intensity, angle, and sort our data in different modes. And with the help of that, we can actually get the knowledge of the quantum mechanical behavior like spin, parity, lifetime, all other informations about the nucleus. But we only have these three things. Of course, if you use some specific detectors for the charged particle, you can look out for the particles itself. If you are using some quadrupoles there, you can go for the detection of the mass of the particle. But again, those 4 or 5 parameters only. So nothing we can say about the quantum mechanical parameters directly in the experiment. So ultimately, while doing the experiment, we just have the target nucleus. We have a beam from the accelerator. We heat it with this beam. They get fused. Compound nucleus is formed, and then this decay would take place. So initially, these particles, protons, would be ejected out. After that, nucleus will be decaying through emission of the gamma rays. These gamma rays are what we generally catch. This is, I can skip. So where to perform the experiments? Of course, for India, I am showing. So you can see these symbols for nuclear hazard. These symbols wherever have been shown. So New Delhi, you have Inter-University Accelerator Center. Mumbai, you have TIFR, and then VCC Kolkata. So at Mumbai and Delhi, you have the peloton, almost around 15 megavolt pelotons are there. And in VCC, we have the cyclotron, that old aged cyclotron, which was first planned by Professor Meghnad. Then there are different stories. I am not going into those details. And very recently in Saha Institute, one new facility is going to come up in terms of dedicated nuclear astrophysics based studies. So these three are prominent stations where one can do the nuclear structure based experiments. Other than this, we do have other small pelotons like in Guru Ghasidas University, Bilaspur, Chhattisgarh. Then one is there in IOP, Bhubaneswar. One Van de Graaff generator used to be functional sometime in BHU itself. One small accelerator is there in IIT Kanpur. Then Punjab used to host one small cyclotron. Okay, so these are the centers. Some photographs are there. I am not going into all those technical details. That will take another 1 or 2 talks, 2 more talks. So this is this peloton building of IUC. This is the peloton building of IFR, and here you can see the inside story of this peloton building. This is the entire cylindrical chamber, and you can understand the height of this. You can see the ocean behind this one, and these are the buildings maybe 4 or 5 stories tall. So beyond this you have this one. Okay, so one can do some eye estimation. This is the schematic diagram of the peloton. So we generally keep that whatever trajectory we want, the ion source over here, do some small acceleration along this, bend it with electromagnetic fields, and then put it inside. A very high positive charge of the order of 15 megavolt sits at the center. Negative, singly charged negative ions are being accelerated here, and then we strip off those electrons, and then it becomes positive. So it is again repelled by the positive center. It goes below, and then you have different beam halls over here. Each hall is dedicated for each of the scientific fields. One is for nuclear, one is for material science, one is for biological studies, etc. So those beam lines go out, and there one can perform the experiments accordingly. Sometimes this peloton is also coupled with something called LINAC, that is linear accelerator. Here it is, I guess, the commissioning of photograph of commissioning of LINAC in TIFR. Professors are there, and you can see Dr. APJ Abdul Kalam over here. He visited the center at that point of time. And next, so I was talking about the beam hall. So inside it looks like this. So we have this 4-pi directional detector array. So this is called INGA, Indian National Gamma Array. So here one beam line comes in. You can see different beam lines are over here. Those are dedicated for different sort of studies in different fields. And before designing of this entire system, one needs to simulate the whole thing. Otherwise, one can't make the proposal for this type of system. So one can simulate this real-time detection system and then go for efficiency check and other things. And that is why initially I told that simulation nowadays form a very big chunk of the studies and analysis. Okay. This is the IUSC setup. So ultimately it looks like this 4-pi directional detector array. And these are all gamma detector arrays being connected with this electronics. And with this, I come to the end of my talk. Thank you, all of you, for your patience. Thanks.
Thanks a lot, Somnath. This was really a nice and beautiful talk, really a picturesque one. So we learned a lot from you. Especially, I was very excited to see your when you saw the similarity between the planetary spin and the spin of nucleus. So that was really exciting for me since I'm from the astrophysics background. So the talk was So talk was really nice. And you told that for your experiment, usually you have as output only the intensity and count and some kind of angle for the gamma rays. And the situation is more or less same for us also, astrophysics also. So we have only few photons and their energies and only very few informations. And from there we make the whole lot of things.
Yeah. So I understand that many students are over here. So at least they should understand that whenever we talk about this state-of-art experimental systems, maybe even in CERN. So there also we just have only these 2, 3, 4 parameters. Yeah. And at that point, one should try to appreciate that how people tend to club in all those parameters and tend to probe inside these microscopic systems. So that is really magnificent. Why I started with those planetary motions, because I think whenever human life evolved, means when they started to look around beyond their food and shelter. So I think the first field they explored, that was the stars and the sky. So astrophysics is something which I think started first. And maybe I thought that was the thought behind that. Maybe people will also try to get it, that if I start with these planets, so they will be, otherwise suddenly nuclear shapes nobody would get who is not from this field. Okay.
Yeah, but your talk was really exciting. So I have 1 or 2 questions. The questions are, it looks childish, but these are questions that students have made. So first one is that is it possible to break the nucleus theoretically or experimentally? If so, then what are the consequences? So someone want to break the nucleus.
Yeah, of course you can break it because of course we break it because whenever we need to get this what you call power generation out of nucleus, we do break it. We carry out this fission process. I think this is a textbook problem. You can read it. Their nucleus breaks actually.
That's how we get the bomb, atomic bomb.
Also the bomb. I didn't take the name of bomb because that is the disastrous one.
Understood. So the next question is that I don't know whether it makes sense. Why for changing in lambda we get quadruple or monopole, etc. So.
Okay. Yeah, so those are actually excitation modes, or not excitation modes even if in simple mathematics, one try to expand any relation in different orders. So it will start from 0, then 1, then 2, then 3, then 4. That's all. So it's simple mathematics. It has nothing to do with the nuclear physics. We are just looking at the deformation, and because deformation can have different set of orders, so those orders we are explaining in terms of those modes. And of course, physicists are very clever. They always start with very simple system and then go on to build up onto these difficult systems. So that is why we start with the quadrupole. Of course, I told you that monopole and dipole won't make any physical sense as such. So we start with quadrupole, and then we also impose that symmetry should exist. So we immediately vanish some of the other parameters, and just with the 2 parameters we played around. And okay, nature was kind enough that nature has also generated those prolate and oblate shapes more often compared to other triaxial and other shapes. Okay.
So thanks a lot, Somnath. We really enjoyed your talk. Thanks a lot.
Yeah. Thank you, all of you. Thanks to the audience also. Okay. Thanks, Sabasachida. Okay.
And we have Dr. Pradeep Ghosh, the director of Midnapore City College, with us. So I will request Dr. Ghosh to say a few words to us.
Okay, my greetings to Professor Ghosh, sir. I didn't realize he was here earlier. I directly started my talk. Okay.
Yeah. Sir, are you here? Can you hear me? Probably he cannot hear me. So next, I will move to our last speaker, Dr. Somak Bhattacharyya. We share a great personal relationship from his MTech days. Somak Bhattacharyya has received honors in physics from Scottish Church College. He has a very exciting career. So I'll just say a few things about him. So after finishing his bachelor year from Scottish Church, next he received both Bachelor of Technology and Master of Technology from Institute of Radio Physics and Electronics at the University of Calcutta. You know that the radio physics is a prestigious institute. After that, he had carried out the MTech thesis in a giant meter wave radio telescope at Tata Institute of Fundamental Research, where we basically met. He is the recipient of University Gold Medal due to securing first position in MTech. He received his PhD degree from IIT Kanpur. Since 2016, he is working as a professor in the Department of Electronics Engineering at Indian Institute of Technology, BHU. He has published more than 40 international journals, 40 papers in international journals, and more than 90 research articles in various national and international conferences. He has received the prestigious Young Scientist Award from International Union of Radio Sciences 3 times. Okay, once from Hiroshima, once from New Delhi, and other times from Asia Pacific Radio Science Conference in Seoul. So he has a very bright career. Owing to his contribution in the area of radio sciences, RC has conferred him honorary lifetime membership. Dr. Bhattacharya is an IEEE senior member and has been elected as a Life Fellow of the Optical Society of India. Recently, he has been elected as the Associate Fellow of West Bengal Academy of Science and Technology, as well as Fellow of IETE. Since 2021, he is serving as the coordinator of IEEE Region 10 in the Young Professional Group of MTT Society. His current area of interest lie in metasurface, periodic structures, opto-microwave devices, microwave photonics. So he is one of the best in the field of his study, field of his interest. So that's why I invited him so that you have the great experience today. And today we have one astronomer, one nuclear scientist, and one who is one of the best in the country in electronics. So we have the whole understanding of the various topic in astrophysics. So I will request Somnath, I will request Somak to please start.
Yes, am I audible? Am I audible?
Yeah, you are audible.
Okay, so good afternoon to all. Okay, so Dr. Nag, can you please stop sharing your screen so that I can share my screen? It's showing. Okay. Just let me know once you can see my screen. I am trying to share it out.
Yeah. Now you can share your screen.
Yeah, is it coming?
It's coming.
Now, is it coming? Is it there?
Yeah, one moment, please. Yeah, just a moment. I'm just
Sure.
refreshing it. Mr. Sumant, can you hear me? We cannot see the screen.
Okay. So let me stop sharing it once again. And
no, you share it. You share it. Only then we'll understand when it comes in YouTube.
Just 1 minute. I have stopped sharing it.
Yeah. You share it, please.
Let me reshare. Okay, now I have reshared my screen.
Please.
Now please let me know whether can you see my screen now?
Yeah. Just a moment, please. Yeah, now we can see your screen. Yeah, you can start.
Now with the full, I have gone to the full screen. Can you listen to me? Can you listen? Is it visible? I have moved to the full screen. Hello.
You just start. There will be a little bit delay, but it's visible. Yeah, it's visible.
But I have moved to the full screen now. Can you see?
Don't move to the full screen. Probably there's some problem with the full screen. You just go without full screen.
Okay. I don't know. Yeah.
If it's okay. Yeah, but we can see your screen. Yeah, your full screen I can see.
You can see. Okay.
Yeah.
Okay. So good afternoon to all of you. And first of all, let me thank Professor Somak Bhattacharyya, whom I used to treat my elder brother, Somak Bhattacharyya, who always guided me when I was carrying out my master's thesis in geometry, as he was already told about. So I don't know. So he invited me for this talk. I don't know how much I'll be able to tell or communicate about our things. So what I have decided, I have chosen a topic of some kind of general interest so that the students from different backgrounds, so you people can understand. Okay. So what I am just having this kind in the mind that if you are having a technical background, you are having a knowledge of BTech second year. If you are having a science background, then maybe you are having the bachelor's completed and maybe master's first year or so. So accordingly, I have made my slides. Okay. So I will talk about the high frequency communications over here. And yes, that as my previous speaker has already told you that we are from the IIT BHU Varanasi. So we are situated in the state of UP on the bank of river Ganges. And it is the beautiful ghats that it is for which the Varanasi is famous for. You can see a snapshot over here. And followed by that you can observe that very nice Ganga Aarti, which is very much famous during the evening time in Varanasi and in the ghats of river Ganges. And yes, our institute, it is co-located in BHU, and it is the largest, I should say, the largest academic area or largest academic premises in Asia. Okay, and yes, so how big it is? Well, you have to take an auto rickshaw to fly between one end to another end. And here you can see our main gate. And if you are able to read the Devanagari script, you can see over here the Kashi Hindu Vishwavidyalaya is written over here, and autos are standing over here. Okay. Can you see this cursor? Is it okay? Is it visible? Hello, is it visible?
Yeah, your cursor is visible. Yeah.
Okay. And slides are also moving, right?
Slides are moving. There's some delay, but it's moving. Yeah.
Okay, fine. Thank you. And yes, our institute, it is situated within the campus of BHU, as I have already told you. And yes, once you are coming from the main gate, so main gate is somewhere in this particular direction. It is somewhere over here. And as you are entering from here, you will find a beautiful temple over here of Lord Vishwanath, which basically segregates the IIT campus or IIT area from the BHU area. Okay. And we are here over here, and we have become IIT in 2012. And yes, so now I am coming to the technical portions of my talk. So let me tell you that, well, what do we mean by communication? I think communication, it means that you are having some kind of transfer of information, or basically you basically want to convey some messages from the source to the destination. This is known as communication. For example, if you can see over here, that in this case, that in the earlier days, for example, in this set, you can see that you are having several religious symbols, okay, which basically convey some messages, okay. Here you can see that your ancient days hieroglyphic scripts or scripts written on the papyrus, okay, that as you have studied in our ancient days, earlier on school days history. And also you can see the first telephone that which was invented by Sir Alexander Graham Bell. So these are some earlier days of communication. Now, whenever people use this kind of things, so what they used to do, that at that time people could not, they could not speak out. So they used to communicate by having some kind of painting so that the information can be transferred in an efficient manner. And recent days, we are all having this kind of equipments at our home, or this one. So this is basically a television. Okay, here you can see a FM receiver, and here is a laptop, which perhaps many of you are using that to listen to this particular talks. Okay, and here by capturing all these ones, one used to have some digital camera, which was very much popular in the last decade, but nowadays, all of us, in fact, many of you perhaps are using this particular device to access all these ones. This is simply a smartphone. Okay. So what is happening that people are integrating a number of features into a single device. So here comes the issue of the multifunctionality. Okay. Now here, let me tell you, once the communication becomes popular, so one of the important factor is the electromagnetic spectrum. So what do we mean by electromagnetic spectrum? The spectrum, this particular term means with respect to frequency. Okay, so here what you can observe, that is the distribution of frequency in a larger scale. You can see that in this scale you are having it with respect to wavelength, and you can simply, just let me do one thing. Yeah, you can simply convert that, that lambda equal to C upon F. So as the frequency increases, so your lambda, that will go down. Okay, so here in this case, what you can find, that in this one, that lambda is going down, or in other words, the frequency, you can see that here the frequency that goes up. So basically in this direction, from lower to upper end, you are having the increase of frequency. Okay, so this is basically the distribution of the electromagnetic spectrum. Okay. Now let me tell you that the use of the different frequency bands in the spectrum. At the very low frequency, we are having the audio frequency, or AF, which has been used for the telephony application. Okay. Next to it, we are having the very low frequency, or VLF, which has been used for the long distance communication. Okay, from 10 kilohertz to 30 kilohertz. Okay. Then we are having the low frequency used for the navigation application from 30 kilohertz to 300 kilohertz. What do we mean by this particular term of navigation? Suppose you know 2 points very accurately, x1, y1. What I want to make, that suppose you know x1, y1, z1, and similarly you know that what is x2, y2, z2. Now depending on this one, you try to compute a third point, okay, over here, which is basically x3, y3, z3, in terms of this x1, y1, z1 and x2, y2, z2. Okay, this is known as navigation, used for any kind of navy application. Okay, then we are having the medium frequency lying between 300 kilohertz to 3 megahertz, used for the radio broadcast. Now this radio broadcast, what I mean to say, the earlier days AM broadcast. Okay, so if you consider a AM background, or AM, I should say the range, it lies between 550 kilohertz to 1650 kilohertz. Okay, this is the range of a typical AM signal. Okay? So this can be used for, this can be considered for a radio broadcasting application, the medium frequency. After that, one can have the high frequency, or the walkie-talkie, which has been used from 3 to 30 megahertz. Followed by that, you are having the very high frequency for 30 megahertz to 300 megahertz, used for TV or FM. So TV means I am talking about the earlier days Doordarshan television, okay, not the current days satellite television. For example, if you consider the TV, okay, the frequency band is between 61 to 68 megahertz, okay, while in the another case for the FM, you can consider this is between 88 to 108 megahertz. So there are two distinct frequency bands which are lying over here. Okay, And after that, you are having 300 megahertz to 3 gigahertz, which is known as the UHF or ultra high frequency, known for the radar application. And then you are having the super high frequency for the satellite. And then you are having 30 to 300 gigahertz for the extra high frequency. Now, these three frequency bands from 300 megahertz to 300 gigahertz, if you convert it into wavelengths, so you will find it from 1 meter to 1 millimeter, and this basically gives you the microwave band. This particular frequency range provides you the microwave band, which is having the 1 millimeter to 1 meter. But yes, that nowadays there is some kind of modification of this particular definition. I will come to that one very soon. Now, the next one is the optical range. This optical means I am covering the all this one, like the visible, the infrared, okay, and the ultraviolet one. Now, if you notice, you can have a gap in between these two, which is basically the terahertz gap. I will come to this point later in my talk. So in a communication basic system, what you need a source, okay, from where the signal has to be transmitted. You need a transmitter which will give you or which will provide you the modulation, and the modulated will be transmitted through a transmission medium, and then it has been received by a receiver where you are having the demodulation, and followed by that one it has been received at the destination end. And here you can have that in a typical communication system, there are several figures of merits. So first of all is the signal to noise ratio, or SNR we call it. That is how much larger is the signal power with respect to the noise level. And with that one you can also quantify what is the noise figure in the system, and also that what is the channel capacity associated with it. So if you are having the channel capacity over here, C equal to B log to 1 plus SNR. So if the SNR or signal to noise ratio remains constant, what is happening? If I am having a bandwidth or B increases, the channel capacity, it simply gets enhanced. So the very thing, the first thing that why people are interested for the high frequency communication. At the high frequency, basically once you are moving up in the high frequency domain, basically what you do, your carrier frequency, that basically shoots up. And once there is a shooting up of the carrier frequency, what you can consider the bandwidth, okay, that also shoots up. And this can be considered as proportional to FC by 10 as a thumb rule. So this where the FC is nothing but the carrier frequency. And enhancement of bandwidth provides you the increment in the channel capacity. So this is the simple, simple relationship between the channel capacity and the carrier frequency, so that one can go with the higher frequency applications. Okay. Now after that, in the high frequency, mainly we are talking of the microwave and the optical range, as I have told you. And in between that, you are having the terahertz domain. Okay. And this terahertz domain, I can say this is between, this is 0.3 to 30 terahertz. This is also known as terahertz gap or terahertz window. I will come to some of the salient feature of this domain in the later half of my talk, or at the end of my talk. So once we are talking of this wireless communication, so here are some of the pioneers in this field who have made significant contributions. Okay, I hope that all of you have heard about all these three great personalities, and the middle one is we are proud that yes, from India also we had a very good representative as Acharya Jagadish Chandra Bose, who had made significant contribution in this domain in the late 1890s. Okay, and in fact, here I am showing you that he had how that the Jagadish Chandra Bose, that he had made this particular experimental setup, and he has carried out this experiment in Presidency College, Kolkata, and also later half in the what is known as the current day as the Bose Institute, that which is very much, which is just adjacent to the building of the Calcutta University Science College campus, okay, in Kolkata. So there he has made this particular experiment. You can see the experimental setup over here, and just think of that during those days, India was not independent. Okay, we were basically governed by British. And those days that he was invited at Royal Institution London after a successful show in the Town Hall, Kolkata, regarding the demonstration of the wireless communication over a short distance. And he had made it at 60 millimeter. Sorry, at 60 gigahertz. Okay. And here you can see that here these are the towers which has been used by Marconi. And what Marconi had done, he had made up over a longer distance. And then he had patented that idea. so that later he has claimed it for a Nobel Prize. Okay, and let me just tell you one thing in this regard, that you notice this one. This one was demonstrated in 1897. Just 100 years later, you can see that it is one of the, just a snapshot from one of the papers. Okay, you can see the paper, that what is the abstract is written there. Just 100 years ago, J.C. Bose described to the Royal Institution in London his research carried out at Calcutta at millimeter wavelengths. He used waveguides, horn antennas, dielectric lenses, various polarizers, and even semiconductors at frequencies as high as 60 GHz. Some concepts from his original 1897 papers have been incorporated into a new 1.3 millimeter multi-beam receiver now in use on the NRA 12-meter telescope. Just to think of his legacy, which has been, in fact, people have discussed even 100 years later, and what we are calling about the millimeter wave, 5G, all those technology, whatever we are discussing nowadays, he had thought of nearly 125 years ago from today. And let me just, it's a paper cutting. So this was in a paper cutting in 2012 in one of the famous times, that here that you can see that US agency is nothing but, this US agency is IEEE, which stands for the Institution of Electrical and Electronics Engineers. Okay, so this is the largest community in the field of electrical and electronics engineer, and they recognize the effort or the work carried out by J.C. Bose as well as C.V. Raman in 2012. So they are the first Indian, or these are the first Indian to be recognized by IEEE. This was huge. And here I am showing you the plaque which was given by them. And you can see over here that first millimeter wave communication experiments by J.C. Bose during 1895 to 1896. Sir Jagadish Chandra Bose in 1895 was demonstrated at Presidency College, Calcutta, India, transmission and reception of electromagnetic waves at 60 GHz over a distance of 23 meters through two intervening walls by remotely ringing a bell and detonating gunpowder. For his communication system, Bose developed entire millimeter wave components such as a spark transmitter, coherent dielectric lens, polarizers, horn antenna, and cylindrical diffraction grating. And it was handed over to the authority in September 2012. Just to imagine that how well ahead he was in for his time, and he didn't have sufficient funding and all those ones. Yes, so we cry out for funding and everything for today. Just think of that, what that gentleman had done some nearly 125 years ago, and that's why he's J.C. Bose. Okay, and later on, this legacy continued in India, the research on wireless, and the first person I should say that who has successfully done that, his name is Shishir Kumar Mitra. He was a professor in physics in Calcutta University during those days, and he started the specialization of wireless communication in Calcutta University Physics Master's course. Okay, and later on, he had made some extensive research or exclusive research on the upper atmosphere regarding the propagation of the electromagnetic wave. So this upper atmosphere, this is one of the, you can consider the Bible in this particular field of propagation. And he also was the instrumental to set up the first research center in India, okay, and which later offers the degree course in the field of electronics and communication. And it is nothing but my own alma mater of Institute of Radio Physics and Electronics in University of Calcutta, and it was established long back in 1949. And advanced research in this high frequency has also continued in other parts of India within a very small part of time. And this is the CD Pilani. It is established in 1953 under the proper guidance or vision of Shanti Swarup Bhatnagar, okay, after which the famous Bhatnagar Prize has been named, okay, for the significant contribution in this domain, okay. And also that within that period, the first IIT in India that was also set up in IIT Kharagpur in 1951 for carrying out some advanced research in all the fields. So just to think of, within the very small short of time right after the independence, India had come up with so many great institutions. Okay. Yes, now if we come, as I was just discussing a few minutes ago regarding the microwave frequencies, one of the commercial microwave frequency bands, you can say that they have been named as different ones, as you can see, like here, AL, S, C, X, K, U, K, K. So basically what was happening, these terms were coined during the Second World War. And you know that in Second World War that there were two oppositions, right? One is the, you can say that you are having one friendly kind of power, and one is the opposition power. And that's why that they use this kind of code language so that they can communicate among themselves. Okay. And later on, the IEEE as well as the microwave community, they adapted these particular terms so that they can use or they can refer to this particular frequency bands. Okay. And as an electronics engineer, or I should say that as an once you can go with the, you know that the electromagnetic subject, okay, one should be very aware of all these microwave frequency bands. Okay. Now, in the microwave frequency band, one of the important application is satellite application. So what is happening? You are having two stations over here in the situated to the ground. From one station, the signal has been, in fact, it has been, uplinked, or I should say it is being sent to the solar object or some kind of satellite. And then it has been received over here and subsequently processed and then get reflected back. So this, by this one can have some kind of proper transmission over a distant one. And here, these are known as this is known as it has been sent, I can say like this way, this is known as up, or I can say like this way, this is known as uplink. And while you are coming from the satellite to the down station, this is known as downlink. So uplinking and downlinking are the two important steps in a satellite communication. And in this particular domain, yeah, in India also the first satellite which was made in 1975, that it was named as Aryabhatta, and the person who had a great vision regarding this is none other than Dr. Vikram Sarabhai, who basically started the concept of ISR. And in later in 2008, in fact, this was set up, this space network antenna in the satellite for some satellite application. It is in Bayalalu, close to Bangalore, and it was operating in X band of frequency, that is between 8 to 12 gigahertz. You can see basically it's a dish of something 32 meter. Okay, and here you can see that yes, that this particular one, you can see that how bigger it was. Yes, this is the during the construction of this particular dish. Okay, and you can see that you can see Professor Ananta Krishnan, that who is one of the legendary figure in India for this particular domain. So he's standing over here with the engineer, okay, Mr. Thepane, okay, that who was instrumental while building this particular telescope. And later he also built up some kind of other telescopes in India, for which he was also famous for. So after this, I am coming to this one, but although I feel that yes, that since people like Dr. Pal is over here, so I should not speak much word over this one. But let me tell you this for the other people, that well, if you observe at our at different frequencies, if you want to observe our for all these the objects, okay, that all these sources, okay, which is present in the sky. In the optical range, you are having a very small window through which you can see by your naked eye as well as by using telescopes. In IR, you are having some kind of very narrow windows. But in the microwave frequency or in the radio frequency, you are having a larger window, and that's why people have chosen this particular window for having that some of the distinct observations. And here, before that one, you are having the opaque ionosphere. What does it mean? For example, if you want to send one amplitude modulated signal or AM signal or earlier days radio signal, what is happening? A signal has been sent from the ground to the sky, and it is getting reflected from the ionosphere, which is acting as an umbrella till a frequency of close to 3 megahertz. Okay, so what you can see that at the very high frequencies, what you are having, the atmosphere is completely opaque. Okay, so you can't send the signal from there. So you need to do some kind of instrumental thing, or you need some kind of instrument which are lying at the space. Okay, and here let me not going into very deep. And yes, it is the study of the universe at radio wavelengths, this radio astronomy, and it was started in 1930s as an offshoot of this development in radio communications technology. And yes, so let me tell you like this way. So basically, astronomy means you are basically studying some kind of objects, okay, some kind of distant objects, okay, and some kind of that's used for different applications. I am not going into details because you people know much better than me about this one. Yes, and at different frequencies, you can have this kind of studies from the gamma ray, IR, or X-ray, or optical, or the UV one. Now, why it is important? As you move to the different frequencies, you can have the emission of the from the different different materials which are only present within this particular object. So from that one, you can say that, well, this particular object is composed of this particular material. For that, you need this kind of observations. Okay, and yes, that what I have started off that that Carl Jansky, he was an engineer in Bell Lab in US. So he's considered as the father of the radio astronomy. So what he used to do, he went to the field to measure some to take some measurements, and what he was observing some kind of pulses which have been received after a certain interval of time. He's used to get some kind of some peak of the pulses, and once it has been found later that it is coming from a some kind of rotating star, okay, which is present in the sky. So this is one of the interesting one, and which basically unfolds a new area of research. And in India also, that this radio astronomy had started, and one person that who was instrumental in this field, okay, I'm showing over here, it was in 1960s, and this person that he has made some significant contribution by using a single dish. Okay, his name is Professor Mrinal Kanti Dasgupta from the Institute of Radio Physics and Electronics and University of Calcutta. And you can see that he had made an image of a distant object, okay, which was later improved by having some kind of better sensitivity, okay, or better resolution. I will come to this point very soon. So some of the telescopes are there, okay, that for example, you can see in the UV range that, well, Subaru telescope is there in Hawaii. In Hubble telescope are lying in space for the higher range of instruments, okay. Then what do we have in a radio telescope? Well, let me tell you, like from very basic point of view, a radio telescope, it is nothing but from, if you are a student of engineering background, let me tell you as simple as a radio telescope is nothing but it is close to a super heterodyne receiver. So what does it mean by this one? So basically you are having, in this case, you are having one antenna from which the signal has been received, then you are having the filters and so on. And for example, the first you are having a PPF, okay, or the band pass filter, so that you are basically you can have the filtering effect over here and reduce the noise. And then what you are having a low noise amplifier, so that the system, the amplifier can be the noise will be reduced over here. And then what you are having a mixer, okay. Here I am having some FLO, that is from the local oscillator, some signal is coming, and here the signal has been received to give rise to some kind of IF frequency. So basically, again, I need some kind of LPA for the low pass filter to generate this FIF, okay, over here, and then accordingly the signal has been processed. So it is similar to the effect of a super heterodyne receiver. I am just going with simpler one. Yes, obviously with the modern day telescope, you are having some kind of other components too. Okay, I'm just going with a very simple one. Now with a single dish, this was I should say the largest single dish telescope in Arecibo in Puerto Rico. But just few months ago, we got a bad news that after the second cable break, okay, that this is now non-functional. Okay, now it has now become non-functional. Okay. In India, the UT radio telescope has come into the picture in 1980s or late 1970s, that where you can do a good measurement at the radio wavelengths. Okay, and now I am coming to one of the very important very interesting things, that, well, once you are having the measurements by using this kind of dishes, okay, one of the very important aspect is that whether you should go with a single dish or you should use an array. Now what is happening, let me tell you, the resolution, you can make it is lambda by d, where d is nothing but the dimension. Okay, now if this lambda by d, what is our aim is this should be as small as possible. Okay, and we should have this one, that how we can make it, this lambda by d should be as small as possible. Well, I am fixing up my lambda. So what I have to make? I have to make my d larger. Now, if I ask you to make an antenna, suppose 1 kilometer long or 500 meter long, is it possible? It is not possible. So what you have to do? You have to make an array. Okay. An array means that suppose you are taking a line and you are having some kind of antenna which have been equally spaced. Okay. So now here, well, so what we are doing that, well, we can have the resolution, or we can enhance the resolution by making the dimension or the footprint of the antenna that is larger. Okay. So this is one of the idea. But the next point is, well, the Earth is rotating in nature. At one time, suppose if the source is over here, and if this is your baseline or this is your antenna line, okay, so you can have the value of D is this one. Okay. But at some instant, you can have it like this. So what you are having some cos theta component. At some point it is like this. So you are having some kind of other values, right? And it is close to 0. So what you have to do? So the idea is that you have to make an arrangement of an array in such a way so that you are having the uniform coverage. So how you can do that? So you have to make a circular one. And how you can make a circular one? The most optimized one by using a Y shape. I can tell you some kind of analogous example is if you are having a ceiling fan. Okay, what does it do? It basically rotates in a in a circular kind of locus. Okay, and what it does, that how many blades are there? There are 3 blades. If you tell me that, sir, can we have it 4 blades? Yes, you may have, but you will require more number of blades. Okay, so the cost will be enhanced. But if you put it in a 120 degree, angular separation, you can have a uniform coverage. Similar to this case also. Okay, so this one, that basically some kind of Y-shaped antenna, arrays have come up as array radio telescope all over the world. Okay, and in India also, that our GMRT, or Giant Meter Wave Radio Telescopes, it is present over there. And here you can see the view of GMRT, okay, the central array that you can see in this particular figure. Okay, I am just showing it, and it is basically situated 90 kilometer north of Pune. Okay, that near to a village known as Khodat. Okay, where this particular antenna has been placed in a Y-shaped pattern. Okay, and these are some of the receivers of GMRT. I am not going into much details over here. Yes, and yes, one of the very, very interesting thing that this is also, you can see in the last year that towards the end of last year. So this also has been regarded as the IEEE milestone status. So this is one of the very prestigious milestone from Indian science perspective. And you can see that this is the 3rd country-based facility. The first one was the work carried out by J.C. Bose, and second one was the work carried out by C.V. Raman, and the third is this particular facility, the building of this particular facility of this GMRT under the TIFR. Okay, and it was the complete brainchild of late Govind Sarup. Okay, and here I can show you the milestone, that plaque which was given to them. That GMRT, consisting of 30 antennas of 45-meter diameter each, spanning 25 kilometers near Pune, India, is one of the largest and most sensitive low-frequency radio telescopes in the world. It pioneered new techniques in antenna design, receiver systems, and signal transport over optical fiber. GMRT has produced important discoveries in domains such as pulsars, supernova, galaxies, quasars, and cosmology, greatly enhancing our understanding of the universe. So this is one of the important issue that for which that it has been awarded the milestone of IEEE. And he is the Professor Govind Sarup, that who has made the significant contribution to, or was brainchild to set up this particular facility in India. And regarding this, if you are interested in this particular literature, is openly available. So you should read this one. So I am just reading the abstract of this one. In this paper, we pay a tribute to the father of Indian radio astronomy, Professor Govind Sarup, BSc, MSc, PhD, FRS, by celebrating his 90th birthday, which occurred on 23rd March 2019, and recounting his remarkable scientific achievements in 3 different regions of the globe: the Indian subcontinent, Australia, and the United States of America. Unfortunately, we lost him in the last year. So this is, I should say that, yes, all of you, especially for all those students, okay, that who are listening to this talk, please read this particular paper. You will really like it. This is my own feeling. And yes, I got a chance to meet him and to share some of the moments, and I can see some of it over here. Okay. And here you can see that the one of the photographs that where Ratan Tata was visiting the GMRT, because it was it is under TIFR. And yes, in this particular place, I have been introduced, or I was introduced to Dr. Sabyasachi Pal, who is basically conducting this webinar. You can see a figure or a particular photograph over here in the GMRT, and you can see, well, this is me, or this was me I believe in 2006 or 7. And this is Sabyasachi in the same time. So this time, in fact, I am just showing you this particular picture just to show that yes, that we were known to each other from that time. Okay, and he guided me a lot during that time for my, for my future career. And yes, that why this is necessary. For example, if you see a Crab nebula, as I was just telling a few minutes ago, that what you can see that at 4 different domains, what you can say that you are getting out that 4 different, the 4 different images. So basically, what you are seeing is not final. At 4 different frequencies, it basically giving some projections of 4 different kind of imaging. So accordingly, you have to do some kind of modeling over there. Then I can show you the Milky Way, that our own Milky Way, if you just observe at different wavelengths, and if you are making the imaging, you are coming out with different kind of outputs. Okay, and the different outputs you can see over here, they are having again no correlation. And you can again say that, well, the Milky Way consists of X, Y, Z, U, V, W, so and so. So many number of elements, so many number of compounds, and so many number of so and so. So those kind of things you can come out from this particular image. Here now I am moving to the next part, the optical communication. So what we are having, well, it is like the same way. Now here, just a minute, please. So here it has been basically taken care. The emission has been taken care by laser. Okay, nowadays, which has been used by used as the optical transmitter. Okay, and then you are having some kind of fiber optic cable, which basically connected to the optical repeaters, so that the signal can be transmitted over a longer distance. Then you are having some photodetector to detect the signal and convert it into the electrical pulses. And let me tell you that in optical frequencies, 2 frequencies are very important. So here you can see one frequency. This is 1.55 micron. Okay, that where you are having the minimum amount of loss. Okay, and this loss is something close to 0.2 dB per kilometer. One standard is there, 0.2 dB per kilometer. Now here what is happening, that next one, so what has been come out as that one, that if you consider the RF frequencies or the microwave frequency, so whenever they have been propagated over the free space, okay, let me tell you like this way, if you are having 2 antennas in free space, okay, if I am having, this is PT is power transmitted, GT is the gain of the antenna, if this is PR, the power received, GR of the gain of the antenna, and if this distance is R, one can show that PR equal to PT GT GR lambda upon 4 pi R whole square. One can show this particular equation. This is known as Friis equation. I'm not going to derive it. Okay, but what you can have, what you can see from here, if you go with the RF signal in the free space, you are having a considerable amount of loss, right? So what is the solution is that, well, you can go with the RF over fiber. So what you can do, you can take an optical fiber through which the RF signal can be propagated. And it has come out with a number of applications, like you can have the broadband mobile communication, okay, or you can have the millimeter wave signal generation in the local oscillator, okay, or you can go with the earth station antenna remote application. So all these ones have come out in this particular domain. And let me tell you another one of the very interesting thing that in multiplexing kind of application, or you can say that in modulation application, one of the important things is multiplexing, where you can combine a number of signals. And here you can consider that in the optical frequencies, you are having this source is they are transmitting at different wavelengths, lambda 1, lambda 2, lambda 3. They have been multiplexed and allowed to propagate over a single channel. and at the receiver end, they have been separated out as lambda1, lambda2, lambda3. And what you can see over here, this T1 lambda1, so this is operating at the wavelength lambda1. So it is coming, okay, and it has been received as the receiver lambda1 over here. On the other hand, a transmitter at this side operating at wavelength lambda2, it has been transmitted from this side, and it is coming through this one and received at wavelength lambda2. So what is interesting over here, if lambda1 and lambda2, if they are not equal to each other, or if they are separated, then what you can have in this case, lambda1 is propagating from left side to right side, while in the other case, lambda2, you can have the propagation from the right side to left side. So you don't have any kind of interference. So this is the kind of advantage you can have by using this wavelength division multiplexing. And this has been taken care of that like this way. So here you can say that wavelength division multiplexing schemes, or they are basically used in EMRT. So how they have been used? Well, you can see some kind of, here basically the lasers are there operating at this frequency, and here the signals have been fed, which is the transmitter, and they have been multiplexed by using this multiplexer, or demultiplexer is shown over here. And then accordingly, you can basically separate it out by using some kind of photodiodes in the receiver end. And here you can see, well, you are having, suppose here what you are doing, that in the front-end system, the signal has been received in two different polarization of the circular polarization to orthogonal polarization, so that you don't have any kind of interference. And then they have been passed through a low noise amplifier over here, and then split it into two powers. One power have been fed to the IF domain, another power has been further amplified and then fed into the transmitter end over here. Two different transmitters operating at two different frequencies, and then you have been multiplexed like this way. And then when it has been passed through an optical fiber, then at the receiver end they have been received, okay, and they have been processed accordingly to separate out these two polarizations. Now this has been carried out, I am telling you, at 1.55 micron. Now this IF, if you see, this IF is operating at 1.3 micron, and here basically why this has been important, because at this frequency you are having zero dispersion, okay, that is phase velocities are same for all these ones. So basically you can see over here that here this particular the property, this has been used, that is 1.31 micron. You can see this has been used from transmission from this end to this end like this way, okay, while 1.55 micron, this has been used from transmission from this end to this end like this way. Since they have been well separated out, so you are not having any kind of interfering effects. So this has been taken care of in the WDM system in GMRT. Okay, and let me tell you one of the very important aspect in this context, that is known as the third order intercept point. So what is happening if you are having the two frequencies which are present in a link, one is F1 and another F2, okay. Now you know that what we are considering, well, all of them are linear in nature, but in practice you are having some kind of non-linearity, and once you are invoking the non-linearity, okay, all the frequency components, especially the third order components, they are extremely, you know, that you can see that 1:1 line, this is basically, we call it 1:1 line, and this we used to call it 3:1 line. Okay, so basically 1:1 line, what is happening, that they are moving in a simple 45-degree angle. The slope is linear in nature. Here also slope is linear, but it is extremely sharp for the third order point. And what is happening, that extremely, if you are having the two fundamental frequencies, F1 and F2, if they are propagated over a same channel, especially the significant intercept, their frequency affected 2f1 minus f2 and 2f2 minus f1. Let me just explain this with a simple example. Suppose you are having two signals generated at 500 megahertz and 501 megahertz, and you are having a 3 dB combiner, which is nothing but you are having half power taken from this side and another power is taken from this side, so that you are having it over here. Now what is happening in this case, in the amplifier end, well, that it will generate these two components, 2f1 minus f2 will be 499 and 2f2 minus f1 is 502 megahertz. Now as you increase this particular power, okay, here, basically, I can say this is my OTX or optical transmitter, and here is my ORX or the optical receiver. So once you are doing this experiment and measured in a spectrum analyzer, well, you can say from this particular figure, so this is my, basically, I can say this is my F1, this is my F2, and while these two one, if you see this particular one, you can say, well, this is my 2F1 minus F2, and this one is my 2F2 minus F1, and they are posing some kind of serious effect on the communication link. So what you have to do, you have to stop before a certain level so that you don't have this kind of effect. So what you have to do, you have taking the measurements. You can see that only in this domain the measurements have been taken in this domain and this domain, and then later on what has been done, you have to make a proper, that interpolation to find out what is the third order intersect point. And idea is you have to operate your device much below to this particular value so that you are operating, you can consider that your device is working at a linear range. So this is one of the very important application in this particular field. And well, so you can say over there, you can see that, well, who don't know me, this is me who was working long back in 2008 in one of the antennas in W4 antenna in GMRT, and doing some kind of measurements over there. And you can see that yes, some signal has been transmitted at 500 megahertz. And you can see that, well, in the analyzer which has been kept in the GMRT. So what you can say that, well, this is your noise level, and this is your signal level, signal which was detected properly at the particular receiver level over here. So this is one of the very important thing that, well, this RF over fiber is feasible because 500 megahertz, this was allowed to propagate over an optical fiber some 15-16 kilometer away. Well, now, as I have told you at the starting of this talk, that I shall talk about the terahertz one. So what is terahertz? So terahertz lying between 0.3 to 30. And if you consider, well, that in this one, that you can take the advantage from both the electronics domain as well as from the optical domain. But the disadvantage is that you don't have the proper source or the proper detector. So what you have to do, you have to customize your device so that you can do the proper measurement. And still, people are making it in an experimental range so that you can't go beyond it. One of the major advantages, once you are going with 1 terahertz, so if you consider the associated energy is 4.1 milli-electron volt, energy equal to h nu, you know that one, right? So what you can have, that you will not have any kind of significant hazardous effect like your X-rays or so, which you may have for any kind of biomedical applications. Okay, you can do some kind of scanning much easily. For example, you can see that some gun has been hidden in this particular bag, or this person is carrying some kind of knife. Okay, so those kind of hidden objects you can easily detect by using this terahertz technology from the security point of applications. Some kind of researches, that's why have been started in high frequencies. Let me be very brief. Okay, so here in our lab we have simulated some kind of antenna which is necessary for these terahertz applications. You can see that at different frequencies it is working, and they are basically giving some kind of good gain at this particular frequencies. Also, we have come out with at the high frequencies some kind of research. Okay, in the megahertz domain, in the gigahertz domain, we can see that some kind of wearable antenna design. Okay, and what we can see over here, well, they are giving some kind of good patterns. Okay, and also we are producing some kind of antenna in the high frequencies. Okay, this also we have studied for some kind of other applications. Okay, by using some kind of gain enhancement of an antenna. Okay, and also another wearable device we have designed, and what we have come out, you can see that whenever you are going with the wearable device, you don't want that any kind of back radiation or towards the body of the particular person that who wears that antenna, on whose body this particular antenna will be implanted, should have minimum effect. And that has been observed from here. You don't have any kind of back radiation from here, and we are still working on it. Okay, so we have also designed some kind of filters, some kind of band stop filter, as well as band pass filters. Let me tell you, all these works have been carried out by some of the interns that who had visited me during the summer vacations in 2018 and 2019. Okay, so basically, what I used to do that, well, if you were that serious, sincere enough, within a period of 2 months, if you want to just spend with me in our lab, you are most welcome. Just approach us through a through proper channel and do the processing, and then you can do the work. And let me tell you that just few days ago, this work was accepted for presentation in the upcoming RC General Assembly. This work was carried out by one of our BTech students that who has just graduated this year. So basically what he has done, he has designed a filter, okay? And what he has done, basically he has developed, okay, that what should be the dimension of the filter to choose a particular frequency. So accordingly, what he has done, he had made this one by using some binary search algorithm. What he has done, the complete, I should say the numerical space, he has been divided into 2 halves. And accordingly, he is determining the cutoff frequency. And again, that within that 2 halves, you are going with finer, the finer division and so on. So accordingly, he has tried to make some kind of, numerical algorithm he has used for making a better, I should say that better or easier approach, that for what will be the dimension to make out a filter, suppose working at 1 terahertz or 2 terahertz with a simpler structure. So that has been taken care of by him. Okay, and this work was appreciated. And also, let me tell you that he has won the Best Paper Award or Best Project Award. Okay, in a presentation organized by IEEE Antenna Propagation Jaipur's chapter just a month earlier. And before I end up, that I must say, or I must acknowledge the summer interns who have worked with me over 2018 and 19. Last year, unfortunately, we didn't have any kind of interns, okay, due to the COVID pandemic. This year, we have just started, and some of them are working with me, okay. And I must not forget the contributions made by my students, okay, that from different capacity, maybe from some of them are from MTech, some of them are and they have graduated. One of them are from PhD and graduated. Some of them are pursuing PhD. Some of them are pursuing MTech. And we have some kind of external students also that who had worked with me to come up with some kind of interesting results, okay. And also I must thank that some of the funding which I have received from ACRB in Government of India, as well as from my own institute for kind of starting startup research grant. And I also should acknowledge my collaborators with whom I have worked in different capacities, okay. And we have come up with some kind of excellent researches, okay. And we are still trying to work some kind of better results, okay. We are working on it, okay. And thank you very much for your talk, and let me thank you very much for your patience. I must say that this is the campus. You can say that is again. Let me come back to the the top view of the temple, that which is basically segregating the IIT campus. And thanks very much for your patience. This is my website that for which you can visit and you can contact me. Yeah, thank you.
Yeah, thanks a lot, Somak, for your beautiful talk. It was really marvelous. So your talk was clear enough, so there was not much room for questions. So a comment, you were showing the picture of the JCBOS instrument. So it just gave me some of my memory. Was someday when I was in Pune, in GMRT site specifically, in the science day, that particular instrument traveled from Boston Institute from Calcutta to Pune for the science day. And I was in charge of that instrument for 2 days.
Oh,
so
wonderful.
So it was. I really felt fantastic to actually touch that instrument. I was feeling shy to touch it.
It's an honor.
So because I can understand the value of this instrument and another instrument by which JCBOS proved that there's a life and the growth of the plants.
Yeah.
So these 2 instruments actually flew to GMRT site for 2 days that science day So that was really a nice memory. I forgot it. Just your picture reminded me that thing. So thanks for that. So your talk was really beautiful. So one question from one of our students. So he's asking that what is the next technology which will be used for the future communication? What will be the best technology in coming days, which will be used for future communication as per your?
Okay, for example, in the terahertz domain, that some works have been already started in the experimental stage, and in fact, some simulation work had already come up. Okay, for example, that yes, so yeah, I mean, there are different technologies out there. For example, one can go with that. Already, people have started working towards 6G or 7G applications already. And if you just think of that, 5G has not been established till now, but what people have called for 6G or 7G. Why? Because you have to employ the terahertz range, and in the terahertz, the main important thing is, as I have mentioned, as you are moving up in the frequency scale, you can employ or you can exploit enormous bandwidth.
Yeah, so 6G is coming, and then 7G, and we'll have a better and better facilities. Yeah. So but again, I don't know whether we need that much. But yeah, dil mange more, so that's okay. So yeah. So thanks a lot, Somak, to be with us. You had really a short time, and you readily agreed to give a talk. So thanks for that. And thanks to all the audience for your patience. All the talks was for you. So thanks for be with us. I just like earlier, I promised that we will have more such talks. Next time we are planning to have some of the talks from our international speakers. So next time we are going to have some of the talks from our some of the best from the international community. And this time we have the 3 of the best scientists of their respective fields with us. So all of you who is with us, thanks a lot. Yeah, thank you.